In September of 2015, a faint ripple, thinner than the width of a proton, passed through two detectors in Louisiana and Washington, and for the first time in human history, we heard the universe tremble. That whisper, born from two black holes spiraling into one another more than 1 billion years ago, traveled across the cosmos at the speed of light, stretching and compressing the fabric of space itself by the smallest measurable amount, and yet it changed everything we thought we knew about how to listen to the sky. For a century, Einstein's equations had predicted these waves, these gentle distortions in spacetime, but no instrument on Earth had ever been sensitive enough to catch them until that autumn afternoon, when silence finally broke. If these quiet hours help ease the mind toward rest, subscribing is a simple way to find more. And so, with the hum of lasers and the patience of decades, the story begins here. In the autumn of 1915, in a Berlin that had grown quieter under the shadow of the Great War, Albert Einstein sat working in his study, turning over in his mind a problem that had consumed him for the better part of a decade. The city around him was rationing food, the young men he had known were away at the front, and yet Einstein, who had never been much interested in the affairs of nations, found himself deep in contemplation of something far more vast and, to him, far more pressing, which was the fundamental nature of space and time themselves. He had been struggling with his theory of gravity, this grand attempt to replace Newton's elegant but incomplete picture with something deeper, something that would explain not just how objects fall but why the universe holds together in the way that it does. And in November of that year, after years of false starts and abandoned calculations, after filling notebook after notebook with tensor equations and geometric arguments, he finally arrived at what we now call the field equations of general relativity, a set of mathematical relationships so compact they could be written on a single line, yet so profound that physicists are still unpacking their consequences more than a century later. What Einstein had discovered, or perhaps constructed, was a new way of thinking about gravity altogether. In Newton's universe, gravity was a force that reached instantaneously across the void, tugging at planets and stars and apples falling from trees through some invisible mechanism that Newton himself admitted he did not understand. But Einstein proposed something quite different. He suggested that what we experience as gravity is not a force at all, but rather the consequence of matter and energy bending the very fabric of space-time itself, so that objects moving through this curved geometry appear to be attracted to one another, much as two marbles rolling on a stretched rubber sheet might curve toward a heavy ball sitting in the center. This was not merely a different description of the same phenomenon, it was a fundamentally new picture of reality, one in which space and time were not the fixed, unchanging stage upon which physics played out, but were themselves dynamic participants in the cosmic drama, shaped by the matter they contained and shaping in turn the motion of that matter. Having completed this monumental work, Einstein did not rest, for the equations he had written down contained within them a universe of predictions waiting to be extracted, and he set about methodically exploring what his theory implied about the world we observe. In 1916, just months after presenting his final field equations to the Prussian Academy of Sciences, he published a paper examining what would happen if spacetime were disturbed, much as the surface of a pond is disturbed when you drop a pebble into still water. What he found, through a series of careful mathematical approximations, was that his equations predicted the existence of ripples in spacetime itself, waves of gravitational influence that would propagate outward from their source at a finite speed. And that speed, his calculations showed, was precisely the speed of light, that fundamental cosmic speed limit that nothing with mass can reach and nothing carrying information can exceed. These gravitational waves, as he called them, would be produced whenever massive objects accelerated, whenever stars orbited one another or matter collapsed or any of the countless violent processes that occur throughout the universe played out. It is worth pausing here to appreciate just how remarkable this prediction was, and how uncertain Einstein himself felt about it, for the mathematics of general relativity is notoriously difficult, and even Einstein, who had invented the theory, was not always certain what it was telling him. In that original 1916 paper, he made a mathematical error, a factor of 2 that crept into his calculations through the complexities of coordinate systems and approximation schemes. He caught this error and corrected it in a subsequent paper published in 1918, but the fact that such a mistake could occur at all, that even the creator of the theory could stumble in its application, gives you some sense of the treacherous mathematical terrain that physicists were attempting to navigate. The equations of general relativity are non-linear, which means that solutions cannot simply be added together to build more complex solutions, and they are written in a language of differential geometry that was, in 1916, unfamiliar to most physicists, a language of curved spaces and transforming coordinates that bent the mind as thoroughly as gravity bent spacetime. This mathematical difficulty gave rise to a controversy that would persist for decades, a debate over whether gravitational waves were a real physical phenomenon that could in principle be detected, or whether they were merely what physicists call a coordinate artifact, a mathematical ghost that appeared in some descriptions of spacetime but had no physical substance. To understand this concern, you must appreciate that one of the fundamental principles of general relativity is that the laws of physics must take the same form regardless of what coordinate system you choose to describe them in, which means that many different coordinate systems can be used to describe the same physical situation, and some features that appear in one description may vanish entirely in another. A wave that seems to propagate in one coordinate system might, when you transform to a different set of coordinates, reveal itself to be nothing more than a peculiarity of your mathematical description, no more real than the ripples you might see in a photograph of a straight stick half submerged in water. This coordinate system confusion, as later physicists would call it, plagued the study of gravitational waves for a generation, and even Einstein himself was not immune to its effects. Indeed, Einstein's own views on gravitational waves underwent a remarkable evolution, a journey from confidence to doubt and back again that illustrates just how difficult these questions were. In 1936, 20 years after his original prediction, Einstein wrote a paper with his colleague Nathan Rosen that appeared to prove that gravitational waves could not exist after all, that any apparent wave solution to the field equations could be transformed away by a clever choice of coordinates, revealing itself as merely a mathematical illusion. He submitted this paper to the Physical Review, the leading American physics journal, fully expecting that it would be published and would settle the question once and for all. But the Physical Review employed a practice, still common today, of sending submitted papers to anonymous experts for evaluation, and the reviewer who received Einstein's manuscript found a subtle but fatal flaw in the argument. The paper was rejected, or at least returned for revision, and Einstein, who was not accustomed to having his work questioned in this way, was reportedly rather irritated by the process. He withdrew the paper and eventually revised it, discovering in the meantime that the reviewer had been correct, that what he and Rosen had interpreted as a proof of non-existence was actually a description of a perfectly valid wave solution expressed in unfortunate coordinates. The revised paper, published elsewhere, acknowledged that gravitational waves were real after all, though the episode left lasting questions about just how confident anyone could be in their existence. The English astronomer and physicist Arthur Eddington, who had done so much to bring general relativity to the English-speaking world by leading the 1919 eclipse expedition that confirmed Einstein's prediction of light bending around the sun, was among the skeptics, or at least among those who urged caution. He is remembered for a quip, delivered with his characteristic dry wit, that gravitational waves travel at the speed of thought, by which he meant to suggest that these supposed ripples in spacetime might be nothing more than mathematical fictions that propagated through physicists' calculations without ever disturbing the physical world. Eddington was a careful thinker, and his skepticism was not mere contrarianism but reflected genuine uncertainty about how to interpret the mathematics, how to separate the physical content of the theory from the artifacts of its formulation. This debate continued for decades, with eminent physicists lining up on both sides, some arguing that gravitational waves must be real because the theory predicted them, others countering that until someone could demonstrate a clear physical mechanism by which they would carry energy and affect detectors, their reality remained an open question. Part of the reason this debate proved so difficult to settle was that Einstein himself had calculated just how feeble gravitational waves would be, at least those produced by any source we might reasonably hope to observe. The strength of a gravitational wave depends on the mass of its source and on how quickly that mass is accelerating, and while the universe contains some extraordinarily massive objects, most of them move with a stately slowness that produces only the most infinitesimal ripples in spacetime. Einstein worked through the numbers and found that the gravitational waves produced by ordinary matter, by spinning wheels or vibrating bars or any terrestrial apparatus you might construct, would be so vanishingly weak as to be completely undetectable by any conceivable technology. Even the waves produced by astronomical sources, by orbiting stars or collapsing nebulae, would arrive at Earth having been diluted by their journey across cosmic distances to the point where they would stretch and squeeze any detector by amounts far smaller than the diameter of an atomic nucleus. It was, Einstein concluded, a prediction that could never be tested, a theoretical curiosity that would remain forever beyond the reach of experiment. This pessimism was not unique to Einstein. For the physicists who came after him and who gradually worked through the coordinate system confusion, establishing by the 1950s and 1960s a clearer understanding of gravitational waves as genuinely physical phenomena that carry energy and can in principle do work on matter, shared his gloom about the prospects for detection. The numbers were simply too daunting, the required sensitivity too far beyond anything that existing technology could achieve. When Einstein died in 1955, in Princeton, New Jersey, where he had spent his final decades as a revered but increasingly isolated figure, he went to his grave believing that gravitational waves, if they existed at all, would never be observed, that this particular prediction of his theory would remain forever a matter of faith rather than evidence. It is a gentle irony of scientific history that Einstein was wrong about this, that the detection he deemed impossible would eventually be achieved, though not until 60 years after his death and only through technological advances that would have seemed like science fiction to the physicists of his generation. But we should not judge his pessimism too harshly, for he was reasoning from the best available knowledge of his time, and the path from theoretical prediction to experimental confirmation would prove to be winding and difficult, requiring not just advances in technology but clarifications in the theory itself, a settling of those coordinate system debates and a clearer understanding of what exactly gravitational waves were and how they would interact with matter. All of that lay in the future, beyond Einstein's lifetime, beyond even the lifetimes of many who would contribute to the eventual success. For now, in the years following 1916, gravitational waves remained an elegant theoretical prediction, a mathematical consequence of the beautiful equations that Einstein had constructed during that difficult wartime autumn in Berlin, equations that described a universe far stranger and more dynamic than Newton had imagined, a universe in which space and time themselves could bend and ripple and flow. Whether those ripples were real, whether they carried energy through the cosmos and could someday be felt by instruments of human construction, remained an open question, a mystery that would take decades to resolve and that would require the efforts of hundreds of physicists and engineers working across continents and generations. But the seed had been planted, the prediction had been made, and though Einstein himself would not live to see its flowering, the idea of gravitational waves had entered the scientific imagination, waiting quietly for the day when technology would finally catch up to theory and the universe would reveal, in the gentlest possible way, that spacetime does indeed ripple when massive objects dance. In the early 1960s, in a modest laboratory at the University of Maryland, a physicist named Joseph Weber began constructing something that had never been attempted before, something that many of his colleagues considered impossible, or at the very least, deeply impractical. He was building instruments to listen for gravitational waves, those impossibly faint ripples in the fabric of space-time that Einstein had predicted decades earlier, and he was doing so at a time when most physicists had quietly concluded that such waves, even if they existed, would forever remain beyond the reach of human measurement. Weber did not share this pessimism, and with the patience of a craftsman and the determination of someone who had already survived circumstances far more perilous than academic skepticism, he set about constructing large cylinders of solid aluminum, each one weighing approximately 1,400 pounds, each one designed to ring, ever so slightly, like a great metal bell when a gravitational wave passed through the Earth. To understand the man who would become the controversial pioneer of gravitational wave detection, it helps to know something of the life that came before his work in that Maryland laboratory. Joseph Weber was born in 1919 in Paterson, New Jersey, the son of Lithuanian Jewish immigrants, and his early years gave little indication of the extraordinary path his life would take. He was drawn to physics and engineering, and when the Second World War began, he found himself serving as a naval officer, eventually stationed aboard the aircraft carrier USS Lexington. In May of 1942, during the Battle of the Coral Sea, the Lexington was struck by Japanese torpedoes and bombs, and the great ship was mortally wounded. Weber was among those who survived the sinking, swimming through oil-covered waters as the carrier burned and eventually slipped beneath the waves. More than 200 of his fellow crew members did not survive that day, and one cannot help but wonder whether such an experience leaves a person with a particular kind of resolve, a willingness to pursue difficult things regardless of the odds, having already faced and survived the arithmetic of unlikely outcomes. After the war, Weber completed his doctorate in physics at the Catholic University of America, and he spent time at the Institute for Advanced Study in Princeton, where the presence of Einstein himself must have felt like a kind of benediction for the work that was to come. By the late 1950s, Weber had joined the faculty at the University of Maryland, and it was there that his thoughts turned increasingly to gravitational waves and the question of whether they might, against all reasonable expectation, be detectable. The theoretical framework was clear enough. Einstein's general theory of relativity predicted that massive objects undergoing acceleration would produce ripples in spacetime, disturbances that would propagate outward at the speed of light, but the expected amplitude of these waves, even from the most violent cosmic events, was so small as to seem almost fictional. The stretching and squeezing of space caused by a passing gravitational wave would change the distance between objects by a factor so tiny that it defied easy comprehension, a fraction of the width of an atomic nucleus over the span of a meter. Weber's approach to this problem was elegant in its conceptual simplicity, even if the practical challenges were formidable. He reasoned that a large, solid cylinder of metal, if isolated sufficiently from all other sources of vibration, might be set into resonant oscillation by a passing gravitational wave, much as a tuning fork will begin to hum when exposed to a sound wave of the right frequency. The cylinder would have a natural resonant frequency determined by its size, shape, and the properties of the metal, and a gravitational wave passing through it would, in principle, deposit a tiny amount of energy into the bar, causing it to vibrate at that frequency. By attaching extremely sensitive transducers to the surface of the cylinder, Weber hoped to detect these minute vibrations and thereby record the passage of a gravitational wave. The cylinders he built were substantial objects, each one roughly 2 meters in length and about 1 meter in diameter, machined from solid aluminum with great care to ensure uniformity. They were suspended by thin wires to isolate them from the vibrations of the building and the earth, and they were surrounded by vacuum chambers to eliminate the disturbances caused by sound and air currents. The transducers Weber used were piezoelectric crystals, materials that generate tiny electrical signals when they are compressed or stretched, and these crystals were bonded to the surface of the bars at locations chosen to maximize their sensitivity to the fundamental resonant mode. The entire apparatus was a testament to Weber's ingenuity and his willingness to work at the very edge of what measurement technology could achieve. Throughout the 1960s, Weber refined his instruments, improving their sensitivity, reducing the sources of noise that plagued every measurement, and developing techniques to distinguish genuine gravitational wave signals from the countless spurious events that his detectors recorded. He operated multiple bars, some at the University of Maryland and others at the Argonne National Laboratory near Chicago, reasoning that a true gravitational wave, arriving from some distant cosmic source, would be detected simultaneously by bars at different locations, while local disturbances would affect only a single instrument. This coincidence technique was a crucial part of his methodology, a way of filtering out the noise and isolating the signal. In 1969, Joseph Weber made an announcement that sent ripples through the physics community, though these were ripples of a more contentious kind than those he claimed to have detected. He reported that his bar detectors had recorded coincident events at a rate that could not be explained by random chance, and he suggested that these events were gravitational waves arriving from the direction of the center of our galaxy. The Milky Way's core, Weber proposed, was producing gravitational radiation that his aluminum cylinders were able to detect, a claim that, if true, would have been one of the most significant experimental discoveries in the history of physics. The response from the scientific community was initially a mixture of excitement and caution, as is appropriate when extraordinary claims are made. Other research groups around the world set about building their own resonant bar detectors, seeking to replicate Weber's results and confirm his revolutionary findings. Weber himself continued to report detections, publishing papers that described an unexpectedly high rate of coincident events, far more than the theorists had predicted would be possible given the expected weakness of gravitational waves from any plausible astrophysical source. As the 1970s progressed, however, the mood began to shift. One by one, the replication experiments came back with null results. Groups in Scotland, Germany, Italy, the Soviet Union, and elsewhere constructed bar detectors of comparable or even superior sensitivity, and they found no evidence of the signals Weber had claimed. The expected rate of coincident events due to random chance was carefully calculated, and the independent experiments found no excess above this background. Theoretical physicists, meanwhile, pointed out that if the galactic center were truly emitting gravitational waves at the rate Weber's detections implied, it would be radiating energy at a rate that would have consumed the entire mass of the galaxy in a cosmologically short time, a clear impossibility. The scientific community's verdict was gradual but eventually became clear, and it was not in Weber's favor. His reported detections were deemed to be false positives, the result of some combination of statistical errors, subtle instrumental effects, or unconscious bias in his data analysis procedures. The precise cause of his erroneous results was never definitively identified, but the consensus was firm: Weber had not detected gravitational waves, and his claims could not be supported by the evidence. For Joseph Weber, this verdict was devastating. He had staked his career on this work, had devoted decades to the pursuit of gravitational waves, and had experienced the heady moment of believing he had succeeded, only to have that success taken away by the accumulating weight of negative evidence. His funding was cut, his reputation was damaged, and he found himself increasingly isolated within the physics community, a prophet without honor whose message had been rejected. It would be easy to portray this as a simple story of a scientist who made a mistake and suffered the consequences, but the reality is more complex and more poignant than that. In his personal life, Weber had found companionship with another scientist whose work would eventually prove to be of profound importance. In 1973, he married Vera Rubin, an astronomer whose observations of galaxy rotation curves would provide some of the first compelling evidence for the existence of dark matter, that mysterious substance that makes up the bulk of the matter in the universe yet interacts with ordinary matter only through gravity. Rubin's work, like Weber's, was initially met with skepticism, but in her case the evidence eventually accumulated in her favor, and she is now recognized as one of the great observational astronomers of the 20th century. One imagines that Weber and Rubin understood something of each other's struggles, the difficulty of pursuing ideas that the mainstream scientific community was reluctant to accept, and perhaps there was some comfort in that shared understanding. Weber never accepted that his detections were false, and he continued to work on gravitational wave detection until the very end of his life, refining his instruments, reanalyzing his data, and publishing papers that defended his original claims. He died in the year 2000, still believing that he had been the first to detect gravitational waves, still convinced that the scientific community had been wrong to reject his results. There is something deeply sad in this, the image of a brilliant and determined man unable to let go of a result that the evidence had shown to be in error, yet also something admirable in his persistence and his refusal to be discouraged by the opposition of his peers. The legacy of Joseph Weber is complicated, but it is not without value. Although his detections were almost certainly spurious, his work served as a catalyst for the entire field of gravitational wave research. Before Weber, the detection of gravitational waves was regarded as a theoretical curiosity, something that might be possible in principle but was not seriously pursued in practice. Weber's bold attempt to build detectors and his dramatic, if mistaken, announcement of success drew attention to the problem, attracted funding and talented researchers, and demonstrated that it was worth trying to detect these elusive ripples in spacetime. The groups that built detectors to replicate his results, and who found no evidence of gravitational waves, nonetheless gained valuable experience in the techniques of precision measurement, experience that would inform the next generation of instruments. In the decades following Weber's work, other researchers continued to develop resonant bar detectors, pushing the technology to ever greater sensitivity. Cryogenic bar detectors, which cooled the aluminum or other materials to temperatures just a few degrees above absolute zero, reduced the thermal noise that had limited the earlier instruments and allowed for much more sensitive measurements. Projects with names like Allegro at Louisiana State University, Auriga and Nautilus in Italy, and Explorer at CERN in Switzerland operated through the 1980s and 1990s, achieving sensitivities that Weber could only have dreamed of, yet still failing to detect gravitational waves with certainty. These instruments represented the culmination of the resonant bar approach, and they demonstrated both its potential and its limitations. Eventually, it became clear that a different technology would be needed to achieve the sensitivity required for reliable gravitational wave detection, and attention shifted to laser interferometers, instruments that could measure the tiny changes in distance caused by gravitational waves using beams of light traveling along kilometer-scale arms. But that is a story for another time, and for now it is enough to note that the path from Joseph Weber's aluminum cylinders to the modern era of gravitational wave astronomy was long and winding, marked by setbacks and disappointments as well as by steady progress. Joseph Weber's contribution to this story is that of the pioneer who ventured into unknown territory, who showed that it was possible to try, even if his own attempt did not succeed. He inspired others to take up the challenge, to build better instruments, to develop more sophisticated analysis techniques, and to persist in the face of daunting odds. The gravitational waves that were eventually detected, more than 50 years after Weber began his work, were found by instruments of a different design, but the spirit of determination and the willingness to pursue a seemingly impossible goal can be traced back, in part, to a Navy officer who survived the sinking of a great ship and who spent his life listening for the faint music of the cosmos, played on cylinders of aluminum that rang, or did not ring, in the silence of a Maryland laboratory. In the summer of 1974, a young man named Russell Hulse arrived in Puerto Rico to begin what would become one of the most important doctoral research projects in the history of physics, though of course he could not have known this at the time, as he was simply a 23-year-old graduate student from the University of Massachusetts Amherst, who had been sent to use the Great Arecibo radio telescope for a systematic survey of the sky, searching for pulsars in the quiet patience that such work requires. The Arecibo telescope was an extraordinary instrument, a vast dish measuring 305 meters across, built into a natural limestone sinkhole in the hills of northwestern Puerto Rico, and its immense collecting area made it particularly well suited to detecting the faint radio whispers of distant pulsars, those rapidly spinning neutron stars that sweep beams of radio waves across the cosmos like lighthouse beacons turning in the dark. Hulse had been assigned this project by his doctoral advisor, Joseph Taylor, a professor at Amherst who had developed a keen interest in pulsars and who understood that finding new ones required the methodical examination of many patches of sky, recording the radio signals and searching through the data for the telltale periodic pulses that would indicate the presence of one of these remarkable objects. The work was largely solitary and demanded considerable patience, as Hulse would observe a region of sky, record the data onto magnetic tapes, and then analyze the results using computer programs designed to detect periodic signals buried within the noise. Day after day through that summer, he scanned different portions of the sky, finding pulsars here and there, each discovery adding to the growing catalogue of these objects that astronomers had been compiling since the first pulsar was discovered in 1967 by Jocelyn Bell and Anthony Hewish in Cambridge, England. The process was repetitive but not unpleasant, the kind of systematic searching that forms the backbone of observational astronomy, where one must examine many ordinary things in order to occasionally find something extraordinary, and where the willingness to persist through long stretches of unremarkable data is an essential virtue. Hulse worked through the Puerto Rican summer, the tropical humidity kept at bay by the telescope's control building, his attention focused on the streams of numbers that emerged from each observation session. On a day in July of that year, Hulse's analysis programs flagged a candidate pulsar in the direction of the constellation Aquila, appearing as a source with a period of approximately 59 milliseconds, which meant that this particular neutron star was spinning about 17 times every second, sending out its radio beacon with each rotation. This was interesting but not unprecedented, as pulsars with such periods were known to exist, and the initial detection seemed like simply another addition to the survey's growing list. However, when Hulse attempted to make follow-up observations to confirm the discovery and measure its properties more precisely, something peculiar began to emerge from the data, something that did not quite fit the expected pattern of a typical pulsar. The pulse arrival times, which should have been extraordinarily regular for such an object, seemed to be shifting in unexpected ways, sometimes arriving a little earlier than predicted, sometimes a little later, in a manner that suggested something more complex was occurring than the simple rotation of a single neutron star in isolation. There was a period during which Hulse very nearly dismissed this object from further consideration, as the variations in the pulse timing created a pattern that resembled the effects of terrestrial radio interference, the kind of human-made signals that could contaminate astronomical observations and lead researchers astray. The Arecibo telescope, despite its remote location, was not entirely immune to such interference, and prudent researchers had to be cautious about distinguishing genuine celestial signals from artificial contamination. Hulse came close to setting aside this puzzling pulsar and moving on to other candidates in his survey, which would have delayed or perhaps even prevented the remarkable discovery that was waiting to be made, but something in the data persuaded him to look more carefully, to observe the object again and again over several days and weeks, building up a longer record of its behavior that might reveal whether the variations were truly intrinsic to the source or merely the result of interference. That happened to coincide with his observations. As August arrived and Hulse continued his observations, the picture gradually became clearer, and what emerged was both unexpected and profoundly significant. The variations in the pulse arrival times were not random noise or interference, but instead followed a regular pattern that repeated with a period of approximately 7 hours and 45 minutes, and the nature of this pattern was precisely what one would expect if the pulsar were not alone but instead were orbiting around another massive object, the two bodies locked in a gravitational embrace that carried the pulsar alternately towards the Earth and away from it as it completed each orbit. When the pulsar moved towards us in its orbit, the pulses would arrive slightly compressed in time, and when it moved away, they would be stretched out, through the same Doppler effect that causes the pitch of a passing ambulance siren to shift as it approaches and recedes. From the characteristics of this timing variation, Hulse and Taylor were able to determine that the pulsar was in orbit around a companion that was itself extraordinarily massive and compact, and the most natural interpretation was that the companion was another neutron star, making this a binary system containing two of the most extreme objects that stellar evolution can produce. The discovery of PSRB 1913+16, as the system came to be designated according to its coordinates in the sky, was significant enough simply as the first known binary pulsar, but Joseph Taylor quickly recognized that this system offered something far more precious to physics than merely a new entry in astronomical catalogues. A binary pulsar would serve as an exquisitely precise natural laboratory for testing the predictions of Einstein's general theory of relativity, because the two neutron stars were orbiting each other in conditions of extreme gravity that could never be reproduced in any earthly experiment, and the regular pulses from one of them provided a natural clock of extraordinary precision that could be monitored from Earth over many years. Taylor understood that the orbital motion of such a system should be affected by various relativistic phenomena that Newton's theory of gravity could not account for, and that careful measurements of the pulse timing over extended periods should reveal these effects with remarkable clarity, if the observations were pursued with sufficient patience and precision. Among the predictions of general relativity that could be tested with this system was one that related directly to gravitational waves, those ripples in spacetime that Einstein had predicted in 1916 but which had never been directly detected and which some physicists still regarded with uncertainty. According to general relativity, two massive objects orbiting each other should continuously radiate energy in the form of gravitational waves, and as this energy is carried away from the system, the two objects should gradually spiral closer together, their orbital period decreasing by a tiny but calculable amount as the years pass. For a system like PSRB 1913+16, with its two neutron stars whirling around each other every 7 hours and 45 minutes, the predicted rate of energy loss could be computed from the equations of general relativity, and the corresponding decrease in orbital period could be predicted with considerable precision. If the observed orbital decay matched the prediction, it would provide compelling evidence that gravitational waves were real and were carrying energy away from the system exactly as Einstein's theory required. The measurement of this orbital decay required patience measured not in weeks or months but in years and decades, as the effect, though significant over astronomical timescales, was minuscule when observed over the span of a human lifetime. The orbital period of the binary pulsar decreases by approximately 76 microseconds per year, which is to say 76 millionths of a second annually, a change so small that it could only be detected through the most careful accumulation of timing data over many years, comparing the actual arrival times of the pulses with the predictions of various theoretical models. Taylor continued this work throughout the 1970s and into the 1980s and beyond, building up an ever longer record of the system's behavior, and as the data accumulated, the agreement between observation and the predictions of general relativity became increasingly precise and increasingly difficult to attribute to anything other than the reality of gravitational wave emission. By the time several decades of observations had been gathered, The cumulative shift in the orbital timing of PSRB 1913+16 matched the predictions of general relativity to within approximately 0.2%, an agreement so close that it left essentially no room for doubt that the system was indeed losing energy through the emission of gravitational waves, exactly as Einstein's theory demanded. This level of precision is quite remarkable when one considers the complexity of the system and the distance from which it is being observed, and it stands as one of the most stringent tests of general relativity ever performed, confirming predictions that Einstein himself had made more than half a century earlier during a time when the mathematical reality of gravitational waves was still being debated and when the prospect of ever detecting them seemed impossibly remote. The orbital decay measured in the binary pulsar has a consequence that extends far into the future, for if the two neutron stars continue to spiral towards each other at the rate implied by the current observations, they will eventually approach so closely that tidal forces will tear them apart and merge them together in a cataclysmic event. Based on the measured rate of inspiral, astronomers have calculated that this merger will occur in approximately 300 million years, a span of time so vast that it is difficult to comprehend in human terms, yet brief enough by cosmic standards that it implies such mergers must occur with some regularity throughout the universe, since the formation of close neutron star binaries cannot be extraordinarily rare if we happen to have found one within our own galaxy. This realization would later prove important when astronomers began designing instruments to detect gravitational waves directly, as it suggested that neutron star mergers might be among the sources observable with sufficiently sensitive detectors. In 1993, the Nobel Prize in Physics was awarded to Russell Hulse and Joseph Taylor for their discovery of the binary pulsar and the subsequent observations that confirmed the emission of gravitational waves. The Nobel Committee recognized that their work had provided the first experimental evidence for the existence of these waves, even though the detection was indirect, inferred from the orbital decay rather than from sensing the waves themselves. Hulse, who had been the 23-year-old graduate student scanning the skies from Puerto Rico, shared the prize with his advisor Taylor, whose persistence in following up the discovery and whose decades of careful monitoring had transformed an interesting curiosity into a profound confirmation of fundamental physics. The award acknowledged that sometimes the most important discoveries come not from the construction of vast new instruments or the development of revolutionary theories but from the patient accumulation of data and the careful comparison of observation with prediction over many years. The binary pulsar remains an active subject of observation even now, as continued monitoring allows ever more precise tests of general relativity and provides an ongoing record of the system's slow march towards its eventual merger hundreds of millions of years hence. The techniques developed to study PSRB 1913+16 have been applied to other binary pulsars discovered since, some of which have proven even more useful for certain relativistic tests due to their particular orbital characteristics, and the field of pulsar timing has grown into a substantial enterprise that continues to probe the nature of gravity and spacetime. Yet the original discovery by Hulse and Taylor retains its special place in the history of gravitational wave science, as the moment when the existence of these waves shifted from theoretical prediction to observed reality, even if that observation was indirect and required the patient accumulation of timing data over years and decades rather than the direct sensing of spacetime vibrations. The story of the binary pulsar reminds us that nature sometimes provides laboratories far more extreme than anything we could construct, and that the universe, if questioned carefully and persistently, will reveal its secrets to those who take the time to listen. A young graduate student with a radio telescope and a systematic approach to searching, combined with an advisor who understood the significance of what had been found and who dedicated years to following up the discovery, together produced one of the most important confirmations of fundamental physics in the 20th century, demonstrating that Einstein's gravitational waves were indeed real and that they carried energy away from accelerating masses exactly as the equations of general relativity predicted, rippling outward through spacetime at the speed of light, too faint to be detected directly with the technology of that era, but present nonetheless, as real as the electromagnetic waves that allowed the pulsar's radio beacon to be detected in the first place. In the early 1970s, a physicist at the Massachusetts Institute of Technology named Rainer Weiss found himself in a situation that would prove unexpectedly consequential. He had been assigned to teach a course on general relativity, a subject in which he did not consider himself an expert, and as often happens when one must teach something properly, he began to think very deeply about aspects of the theory that had previously seemed somewhat abstract or remote. One of his students asked him a question about gravitational waves, those ripples in spacetime that Einstein had predicted more than half a century earlier, and Weiss found that he could not provide a satisfactory answer about how one might actually go about detecting such extraordinarily faint disturbances. Rather than let the question rest, he began to work through the problem methodically, considering what kind of instrument might be sensitive enough to measure the almost inconceivably small stretching and squeezing of space itself. What emerged from this contemplation was a paper, written in 1972, that would become one of the foundational documents in the field of gravitational wave astronomy. In this paper, Weiss described with remarkable thoroughness how one might use laser interferometry to detect gravitational waves, splitting a beam of laser light and sending it down two perpendicular paths, then recombining it to look for the telltale interference patterns that would indicate one arm had become slightly longer or shorter than the other. The beauty of this approach lay in its elegant simplicity of concept combined with its extreme demands on precision, and Weiss did not merely sketch out the basic idea but rather worked through all the various sources of noise that would need to be overcome, from seismic vibrations in the ground to the thermal jostling of atoms in the mirrors to the quantum fluctuations of the light itself. His analysis was painstaking and thorough, running to nearly 100 pages, and it laid out both the promise and the tremendous challenges of such an endeavor. Meanwhile, at the California Institute of Technology in Pasadena, a theoretical physicist named Kip Thorne had been developing his own deep interest in gravitational waves from a rather different direction. Thorne was not an experimentalist but rather a theorist who spent his time thinking about the most extreme objects in the universe, black holes and neutron stars, and the violent events that might cause them to collide or collapse. Through his calculations and those of his students and collaborators, Thorne had become increasingly convinced that there ought to be sources of gravitational waves in the universe that were strong enough to be detected, if only someone could build an instrument sensitive enough to catch them. The key insight was that certain astrophysical events, particularly the final inspiral and merger of two compact objects like neutron stars or black holes, would produce gravitational waves with specific frequencies and amplitudes that fell within a range that seemed, at least in principle, accessible to technology. The third major figure in this early period was a Scottish physicist named Ronald Drever, who had been working on gravitational wave detection at the University of Glasgow using resonant bar detectors before turning his attention to interferometry. Drever possessed an unusual gift for experimental innovation, a kind of intuitive understanding of how to make instruments more sensitive that sometimes operated ahead of his ability to fully articulate the theoretical reasons for his modifications. He developed several crucial techniques that would prove essential for making interferometric detection feasible, including methods for stabilizing the frequency of lasers and innovative approaches to recycling light within the interferometer to effectively increase the laser power without requiring an impossibly powerful light source. His contributions were technically essential, even as his working style sometimes created friction with the more methodical approaches of his colleagues. During the 1970s and early 1980s, these three threads of activity, Weiss at MIT working on the experimental challenges, Thorne at Caltech developing the theoretical foundations, and Drever in Glasgow pushing the boundaries of what interferometers could achieve, began to converge and interweave. Thorne became convinced that interferometric detection was not merely a theoretical possibility but an achievable goal, and he began working to bring together the people and resources that would be needed. In 1979, Drever was invited to Caltech, bringing his experimental expertise and his innovative techniques to the sunny campus in Pasadena, and over the following years, the collaboration between Caltech and MIT began to take shape as something more formal and ambitious. The year 1984 marked the official founding of the Laser Interferometer Gravitational Wave Observatory, known by its acronym LIGO, as a joint project of Caltech and MIT. From the very beginning, it was clear that this would be an undertaking of unprecedented scale for physics, requiring not just clever ideas and talented researchers but also an enormous investment of money and political will sustained over what would inevitably be many years or even decades. The project would require building not one but two enormous interferometers, each with arms stretching 4 kilometers in length, at sites separated by thousands of kilometers so that a genuine gravitational wave signal could be confirmed by its appearance at both locations while local disturbances that affected only one site could be identified and discarded. The early years of LIGO were marked by significant organizational challenges, and the first director of the project, a physicist named Rochus Voigt, faced the difficult task of managing three strong-willed scientists with different working styles and visions for the project while simultaneously trying to convince funding agencies that this ambitious and expensive endeavor was worth supporting. Voigt was by many accounts an effective advocate for the project during a critical period, helping to secure initial funding and attention, but the internal dynamics of the collaboration were often tense, and the challenge of translating brilliant individual contributions into a coherent large-scale project proved formidable. These were years of both progress and frustration, of technical advances achieved alongside interpersonal difficulties that would eventually require changes in leadership and organization. Convincing the National Science Foundation to fund LIGO proved to be a lengthy and uncertain process. The project was asking for an amount of money that dwarfed any previous investment in physics, initially estimated at $272 million, a figure that would eventually grow to more than $1.1 billion over the life of the project. Many scientists outside the gravitational wave community were skeptical, questioning whether the technical challenges could truly be overcome and whether the resources might be better spent on other areas of research with more certain returns. The review panels and committees that examined the proposal subjected it to intense scrutiny, and there were times when the future of the project seemed quite uncertain indeed. The political process of securing funding required not only scientific persuasion but also the support of members of Congress who would have to approve the appropriations year after year for a project that might not yield its promised results for decades. One particularly important ally proved to be Senator J. Bennett Johnston of Louisiana, who recognized that having one of the LIGO installations in his state would bring both economic benefits and scientific prestige to a region not typically associated with cutting-edge physics research. His support helped shepherd the project through the congressional appropriations process at critical moments, demonstrating once again how large scientific projects depend not only on the quality of the science but also on the building of coalitions and the cultivation of political relationships. The selection of sites for the two LIGO observatories involved careful consideration of both scientific and practical factors. The scientific requirement was for the two installations to be separated by as great a distance as possible while still remaining within the continental United States, since the time delay between a gravitational wave signal arriving at one detector and then the other would help confirm its celestial origin and provide information about the direction from which it came. The sites also needed to be seismically quiet, geologically stable, and remote enough from human activity to minimize disturbances from traffic and industry and daily life. After extensive surveying, the collaboration settled on two locations, one in Hanford in the state of Washington, nestled within the Department of Energy's Hanford site with its history of nuclear production, and one near Livingston in Louisiana, surrounded by pine forests in a rural area east of Baton Rouge. The two sites are separated by 3,002 kilometers, allowing a gravitational wave traveling at the speed of light to arrive at one detector roughly 10 milliseconds before reaching the other. Construction began in 1994, and over the following years, the massive vacuum chambers and beam tubes took shape at both sites. Each installation required the construction of two perpendicular arms, each stretching 4 kilometers across the landscape, containing tubes from which nearly all the air had been pumped to create one of the largest sustained vacuums ever achieved on Earth. The mirrors that would reflect the laser beams back and forth needed to be the smoothest and most precisely figured optical surfaces ever made, polished to a perfection measured in fractions of the wavelength of light. The systems for isolating these mirrors from the ever-present vibrations of the ground, from the footsteps of technicians and the passing of distant trucks and the ceaseless microseismic background of the Earth itself, required engineering of extraordinary sophistication. The initial version of LIGO began its first scientific observations in 2002, and over the following 8 years, the two detectors operated through several observing runs of increasing sensitivity and duration. During this period, the instruments achieved their design sensitivity, demonstrating that the fundamental concept worked and that the countless sources of noise could be controlled and suppressed to the levels that had been predicted decades earlier in Weiss's original paper. However, despite this technical success, the initial LIGO detected no gravitational waves. This was not entirely unexpected, as the theoretical estimates of how often detectable events might occur suggested that the initial instruments were operating at the edge of what would be needed, sensitive enough perhaps to catch an unusually close or powerful event, but not quite sensitive enough to guarantee detections during a reasonable observing period. The collaboration then faced a decision that required considerable courage and a willingness to accept risk in pursuit of greater reward. In 2011, both LIGO detectors were shut down, not because of failure but deliberately, so that they could be dismantled and rebuilt with improved technology that would increase their sensitivity by roughly a factor of 10. This upgrade, known as Advanced LIGO, represented a calculated gamble, taking instruments that were working and had cost enormous sums to build and effectively starting over with the hope that the improved version would finally achieve the sensitivity needed for regular detections. Because sensitivity in gravitational wave detection relates to the volume of space that can be surveyed, a tenfold improvement in sensitivity meant roughly a thousandfold increase in the number of potential sources that could be observed, transforming the prospects from occasional lucky detections to routine astronomical observation. The years of the Advanced LIGO upgrade were years of painstaking work, installing new mirrors with even more sophisticated coatings, implementing improved seismic isolation systems, increasing the laser power, and refining every component that contributed to the overall sensitivity of the instruments. The scientists and engineers who had dedicated their careers to this project, many of whom had been working toward this goal since the 1980s or even earlier, continued their patient labors knowing that success was not guaranteed but believing that it was possible. They had spent decades learning how to listen for the quietest whispers in the universe, building machines of almost absurd sensitivity, and now they were making those machines even more sensitive still, pushing further into the realm of the seemingly impossible. By 2015, the Advanced LIGO detectors were approaching readiness for their first observing run. The long journey from Weiss's 1972 paper to this moment had taken more than 4 decades, had consumed more than $1 billion, had required the sustained effort of hundreds of scientists and engineers, and had weathered countless moments of doubt and difficulty. The 3 founders of the project were now in their 70s and 80s, and many of the researchers who would operate the detectors had not yet been born when the theoretical foundations were being laid. The concrete and steel of the observatories stood in their remote locations, the vacuum tubes stretched across the landscape, the mirrors hung in their elaborate isolation systems waiting to catch the faint tremors of distant cosmic events, and the long preparation was nearly complete. The instrument that scientists built to detect gravitational waves is, in many ways, the most sensitive measuring device that human beings have ever constructed. To understand just how extraordinary this achievement is, we might begin by considering what the machine must actually do. When a gravitational wave passes through the Earth, it stretches and compresses space itself by an almost inconceivably small amount. The change in distance that the detector must measure is roughly 1/10,000th the width of a single proton. A proton, you may recall, is already so small that it takes about 10 million of them, lined up side by side, to span the width of a single atom. And we are speaking here of measuring changes that are 10,000 times smaller than even that tiny distance. This is the challenge that faced the engineers and physicists who designed and built the Laser Interferometer Gravitational Wave Observatory, known by its initials as LIGO. The basic design of LIGO follows a principle that has been used in physics laboratories for well over a century, a device called an interferometer. In its simplest form, an interferometer splits a beam of light into 2 parts, sends those parts along different paths, and then recombines them to see how the 2 beams interact. If the 2 paths are exactly the same length, the light waves will arrive back together in a particular alignment. But if one path is even slightly longer or shorter than the other, the waves will arrive slightly out of step, and this misalignment creates a distinctive pattern called interference. By studying this pattern, scientists can measure extraordinarily small differences in the lengths of the 2 paths. The interferometer at LIGO takes this venerable concept and extends it to almost unimaginable precision. The detector is shaped like a giant letter L, with 2 arms stretching out at right angles from a central corner station. Each arm extends for 4 kilometers across the landscape, which is about 2.5 miles in the old imperial measure. At the LIGO site in Hanford, Washington, one arm points roughly toward the north and the other toward the west, while at the companion site in Livingston, Louisiana, the arms are oriented in a similar perpendicular arrangement. This considerable length is essential to the instrument's sensitivity, because a gravitational wave stretches space by a certain fractional amount, and the longer the arms, the larger the absolute change in distance becomes. Even so, when a gravitational wave from the collision of two black holes more than 1 billion light-years away passes through the detector, it changes the length of each 4-kilometer arm by less than 1/10,000th the width of a proton. The instrument must be capable of sensing this change while ignoring all the countless other vibrations and disturbances that constantly shake the Earth. At each end of the L-shaped arms, and at the corner where they meet, hang mirrors of extraordinary quality. These mirrors are not small handheld objects but rather substantial cylinders of fused silica, each weighing approximately 40 kilograms, which is about 88 pounds. Fused silica is a form of glass made from extremely pure silicon dioxide, and it was chosen for its exceptional optical properties and its ability to remain dimensionally stable under the demanding conditions inside the detector. The surfaces of these mirrors are polished to a smoothness that defies easy description. If one of these mirrors were scaled up to the size of the Earth, the largest bumps and valleys on its surface would be only a few centimeters tall. The reflective coating applied to each mirror is so effective that less than 1 photon in every 3 million is absorbed rather than reflected, allowing light to bounce back and forth many times without significant loss. The manner in which these heavy mirrors are suspended is one of the most ingenious aspects of the LIGO design. Each mirror hangs at the bottom of a quadruple pendulum system, which is to say that the mirror is suspended from another mass, which is suspended from another, which is suspended from yet another, forming a chain of 4 pendulums hanging one beneath the other. This arrangement takes advantage of a fundamental property of pendulums, which is that they naturally filter out vibrations at frequencies higher than their own natural swinging frequency. By using 4 pendulums in series, each tuned to swing at a slightly different rate, the system provides an enormous amount of isolation from the small tremors that constantly travel through the ground. The final stage of suspension uses fibers made of fused silica glass, the same material as the mirrors themselves. These fibers are remarkably thin, with a diameter of only about 400 micrometers, which is roughly 4 times the width of a human hair. Despite their slenderness, these glass fibers are surprisingly strong, and they have the crucial advantage of producing very little thermal noise, the tiny random vibrations that occur in all materials due to the motion of their atoms. The mirrors must remain stable in their positions to an almost absurd degree of precision. The target is to control their motion to within 10 to the negative 19 meters, that figure we mentioned earlier representing 1/10,000th of a proton's width. Achieving this requires not only the quadruple pendulum suspension but also an elaborate active control system that constantly monitors the position of each mirror and makes minute corrections using electromagnetic actuators. The control system must distinguish between the genuine signal of a passing gravitational wave, which causes a characteristic pattern of stretching and compression, and the myriad other disturbances that might mimic such a signal. This is accomplished in part by having 2 widely separated detectors, one in Washington state and one in Louisiana, so that a true gravitational wave will produce a similar signal in both instruments within a time delay consistent with the wave traveling at the speed of light across the intervening distance. The arms of the interferometer are not open to the air but are enclosed within vacuum tubes of impressive dimensions. Each tube has a diameter of about 1.2 meters, which is nearly 4 feet, and runs for the entire 4-kilometer length of the arm. The tubes are made of spiral-welded stainless steel and are among the largest sustained vacuum systems in the world. Pumping the air out of these tubes was a considerable undertaking that required approximately 40 days of continuous operation to achieve the necessary vacuum level. The pressure inside the tubes is reduced to about 1/trillionth of normal atmospheric pressure, creating a void more empty than the space between planets. This extreme vacuum is necessary because even the sparse molecules of air at ordinary low pressures would scatter the laser light and disturb the delicate measurements. The light source for LIGO begins as a relatively modest laser producing about 200 watts of power, which is perhaps 1,000 times brighter than a typical laser pointer but still not extraordinary by industrial standards. This initial beam is then amplified and enhanced through a series of optical cavities, which are arrangements of mirrors that cause the light to bounce back and forth many times, effectively multiplying its intensity. By the time the light reaches its full circulating power within the interferometer arms, it has been boosted to an effective power of approximately 750 kilowatts. This intense light is necessary because the precision of the measurement improves with the number of photons available. More photons mean more information about the mirror positions, and thus a more sensitive detector. The laser light used is of a very specific infrared wavelength, invisible to the human eye but well suited to the properties of the optical components. Isolating the mirrors from seismic vibrations is a challenge that required considerable ingenuity. The Earth is never truly still. Seismic waves from distant earthquakes travel through the crust and set the ground in constant gentle motion. Closer to home, human activities create their own disturbances. At the Livingston site in Louisiana, logging trucks traveling on nearby roads produce vibrations that must be carefully filtered out. The site also contends with the unique hazard of alligators, which occasionally wander onto the grounds and must be relocated for both their safety and the safety of the sensitive equipment. Even the distant ocean waves crashing against continental shores create a low-frequency rumble that propagates through the Earth, a phenomenon known as the microseismic background. And in the dry conditions of the Hanford site in Washington, tumbleweeds blown by the wind sometimes strike the perimeter fences, creating small impulses that could, if not properly isolated, disturb the mirrors. The seismic isolation system uses a combination of passive and active elements to reduce all these disturbances by a factor of more than 1 billion at the frequencies where gravitational wave signals are expected. Even after all this careful engineering, there remained a fundamental limit imposed by the laws of quantum mechanics. Light itself is not a smooth continuous wave but consists of individual photons, which arrive at random times according to the probabilistic rules of quantum physics. This randomness creates a noise floor, a minimum level of uncertainty in the measurement that cannot be eliminated by classical means. To push beyond this limit, the LIGO team implemented a technique called quantum squeezing. In ordinary light, the quantum uncertainty is distributed equally between two properties, the amplitude of the wave and the timing of when the wave peaks and troughs arrive. Squeezing takes advantage of a quantum mechanical principle that allows one to reduce the uncertainty in one of these properties at the expense of increasing the uncertainty in the other. For gravitational wave detection, what matters most is the precise timing of the light, so the LIGO engineers use specially prepared squeezed light in which the timing uncertainty is reduced while the amplitude uncertainty is allowed to increase. This squeezed light is generated using a device called an optical parametric oscillator, which creates pairs of entangled photons with correlated quantum properties. By injecting this squeezed light into the interferometer, the team was able to improve the sensitivity by a meaningful amount, pushing the detector beyond what was once thought to be an absolute quantum limit. The two LIGO sites were chosen with great care to maximize their sensitivity and to allow for the confirmation of signals through coincident detection. The Hanford site in southeastern Washington occupies a portion of the Hanford Nuclear Reservation, a vast and relatively isolated tract of land where human activity is minimal. The landscape is arid and flat, with low levels of seismic activity from human sources, although it does experience the occasional tumbleweeds already mentioned. The Livingston site in Louisiana presented different challenges. The land is lower and wetter, with a humid subtropical climate that contrasts sharply with the dry conditions at Hanford. Logging is a significant industry in the region, and the heavy trucks carrying timber create substantial vibrations as they pass along the nearby roads. The LIGO team worked with local authorities and logging companies to coordinate truck schedules, avoiding the most sensitive observing times when possible. The wildlife at Livingston includes the American alligator, a large reptile that can grow to several meters in length and occasionally decides to explore the grounds of the observatory. These animals are carefully captured and relocated to more suitable habitats away from the sensitive equipment. The construction and operation of LIGO represents one of the most ambitious scientific projects ever undertaken. The initial concept was proposed in the 1970s, and serious design work began in the 1980s. The construction of the facilities took place in the 1990s, and the first observations began in the early 2000s. These initial runs did not detect gravitational waves, which was not unexpected given the predicted rarity and weakness of the signals. A major upgrade program, known as Advanced LIGO, was then undertaken to improve the sensitivity by about a factor of 10. This upgrade replaced most of the key components, including the mirrors, the suspensions, the seismic isolation systems, and the laser. The improved detector began operations in September of 2015, and just days later, on the 14th of that month, It recorded the first direct detection of gravitational waves, a signal from the merger of two black holes more than 1 billion light-years away. The signal changed the length of the 4-kilometer arms by about 4/1000ths of the diameter of a proton, a distance so small that it would have been utterly undetectable without the extraordinary engineering we have just described. The mirrors continue to hang in their silica fiber cradles, swaying imperceptibly in their vacuum chambers, waiting to catch the faint whisper of the next gravitational wave to pass through the Earth. On the morning of September 14, 2015, in the quiet hours before dawn had reached the eastern coast of the United States, a ripple in the fabric of spacetime passed through our planet, traveling at the speed of light, having journeyed for more than 1 billion years across the vast and patient darkness of the cosmos. The ripple was extraordinarily faint, stretching and compressing space by an amount far smaller than the width of a proton, and yet it was enough, just barely enough, to disturb the delicate arrangement of mirrors and laser light that the scientists of the LIGO collaboration had spent decades preparing. At precisely 5:51 in the morning, Eastern Daylight Time, the two great interferometers, one nestled among the pine forests of Livingston, Louisiana, and the other set upon the dry plains of Hanford, Washington, recorded a signal that would, in time, come to be recognized as one of the most significant measurements in the history of physics. It is worth pausing here, as we settle into this part of our story, to appreciate the timing of this event, for it carries with it a quality that some might call coincidental and others might simply call fortunate. The advanced LIGO detectors had only just begun their first observing run, or rather, they had not quite begun their observing run at all. The instruments were still in what the scientists called an engineering run, a period of final testing and calibration that precedes the official collection of scientific data. The engineering run had started just 2 days earlier, on September 12, and the detectors were being put through their paces, their systems checked and rechecked, their sensitivities measured and adjusted. No one expected to detect anything of consequence during this preparatory phase. The universe, however, does not consult our schedules, and it sent its messenger regardless of whether we had declared ourselves ready to receive it. The signal arrived first at the Livingston detector, passing through the Louisiana Earth and causing the mirrors suspended at the ends of its 4-kilometer arms to shift by an almost immeasurably small amount. 7 milliseconds later, the same signal reached the Hanford detector in Washington state, having traveled the additional distance between the two facilities at the speed of light. This tiny delay, just 7/1000ths of a second, would prove to be of immense importance, for it confirmed that whatever had caused the disturbance had come from beyond our planet, from somewhere out in the cosmos, rather than from some local source of vibration or interference. The Earth itself is only about 40 milliseconds wide, so to speak, when measured by the time it takes light to cross it, and the 7 millisecond delay was entirely consistent with a gravitational wave arriving from a direction roughly overhead, passing through both detectors in quick succession as it swept across the surface of our world. In Hanover, Germany, where the morning was already well advanced, a young postdoctoral researcher named Marco Drago was sitting at his computer, attending to the routine work of monitoring the LIGO data streams. Drago was part of a team responsible for analyzing the data in near real time, looking for the characteristic patterns that might indicate the presence of a gravitational wave signal. The automated analysis systems had flagged something unusual, and as Drago examined the alert that appeared on his screen, he found himself looking at a signal that seemed almost too perfect, too clean, too exactly like what a gravitational wave from a pair of merging black holes ought to look like. His first reaction was not excitement but suspicion, for the LIGO collaboration had a practice of occasionally injecting false signals into the data stream, a procedure known as a blind injection, designed to test whether the analysis pipelines and the human researchers could correctly identify and characterize a gravitational wave event. Only a small number of people knew when these blind injections occurred or what form they took, and the rest of the collaboration was expected to analyze them as though they were real, only learning the truth after the analysis was complete. Drago sent messages to his colleagues, alerting them to the signal and expressing his uncertainty about whether it might be genuine or whether it might be one of these secret tests. The hours that followed were filled with a growing sense of cautious excitement, tempered always by the awareness that they might be chasing a phantom, a carefully designed illusion meant to keep them honest and sharp. But as the day progressed, and as more and more researchers examined the data, a remarkable fact emerged. The small group of people who had the authority to perform blind injections confirmed, quietly and confidentially, that they had not injected any signal into the data on that day. Whatever the detectors had recorded, it had not been put there deliberately by human hands. It had come from the sky. The signal itself lasted only about 0.2 of a second, a brief chirp of gravitational radiation that rose rapidly in both frequency and amplitude before cutting off abruptly. If one were to convert the gravitational wave signal into sound, shifting it into the range of human hearing, it would resemble a quick upward sweep, a kind of cosmic whistle that climbs from a low rumble to a higher pitch and then suddenly stops. The frequency of the gravitational waves began at around 35 cycles per second, or 35 Hz, which is near the lower limit of what the human ear can perceive, a deep bass tone like the lowest notes of a pipe organ. Over the course of those 0.2 of a second, the frequency rose steadily and then rapidly, climbing through 50 Hz, then 100, then 150, and finally reaching approximately 250 Hz before the signal ended. This is roughly the pitch of middle C on a piano, a note that sits comfortably in the center of the musical range, and the transition from the initial low frequency to this final higher frequency happened in the span of a few heartbeats. This characteristic pattern, the steady rise in frequency and amplitude followed by an abrupt termination, is precisely what physicists had predicted for the final moments of two massive objects spiraling together under the influence of their mutual gravitational attraction. As the objects orbit each other, they emit gravitational waves, and these waves carry energy away from the system. The loss of energy causes the orbit to shrink, which in turn causes the objects to move faster and orbit more rapidly. Faster orbits mean gravitational waves of higher frequency, and so the signal sweeps upward in pitch as the inspiral accelerates. In the final moments, the objects are moving at a significant fraction of the speed of light, completing dozens of orbits per second, and then they merge, colliding and combining into a single larger object. The gravitational wave emission reaches its peak at the moment of merger and then quickly dies away as the newly formed object settles into a stable configuration. This is what the LIGO detectors recorded on that September morning, the final 0.2 of a second of a cosmic dance that had been underway for millions of years. By analyzing the details of the signal, the shape of its waveform, the rate at which the frequency increased, and the maximum amplitude it reached, the scientists were able to determine the properties of the objects that had produced it. The gravitational wave signal carried within it the signatures of its source, encoded in the precise way that the spacetime distortions had evolved over time. What the analysis revealed was extraordinary. The signal had been produced by two black holes, each one a region of space where matter had collapsed under its own gravity to form an object so dense that nothing, not even light, could escape from within its boundary. One of the black holes had a mass equivalent to approximately 36 times the mass of our Sun, and the other had a mass of about 29 solar masses. These were not the supermassive black holes that lurk at the centers of galaxies, containing millions or billions of solar masses, but rather stellar mass black holes, the remnants of massive stars that had ended their lives in catastrophic explosions and gravitational collapse. The two black holes had been orbiting each other, drawing ever closer over countless eons, their mutual gravitational attraction slowly but inexorably pulling them together. At the moment captured by the LIGO signal, they were completing their final orbits, moving at tremendous velocities as they spiraled inward. And then they merged, their event horizons touching and combining, their masses joining together to form a single, larger black hole. The final black hole had a mass of about 62 solar masses, and if you are inclined toward arithmetic, you may notice that 36 plus 29 equals 65, not 62. The missing 3 solar masses did not disappear, for mass and energy cannot simply vanish from the universe. Instead, that mass was converted into energy, specifically into the energy of the gravitational waves that radiated outward from the merger at the speed of light. 3 solar masses, the equivalent of 3 entire stars like our Sun, transformed in an instant into ripples in the fabric of spacetime. It was, for that brief moment, the most powerful event in the observable universe, releasing more energy than all the stars in all the galaxies combined, and yet it was utterly silent and invisible, detectable only through the subtle stretching and squeezing of space itself. The source of the signal, this pair of merging black holes, was located approximately 1.3 billion light-years from Earth. This means that the gravitational waves had been traveling through the cosmos for 1.3 billion years before reaching our planet, having begun their journey at a time when life on Earth consisted only of single-celled organisms, long before the first animals, the first plants, the first multicellular creatures of any kind had appeared. The universe was already ancient when those black holes merged, and yet it was still young enough that the light from that distant event, had there been any light to see, would only now be reaching us. We were listening to an echo from the deep past, a message sent before complex life existed on our world, finally arriving at the precise moment when we had built instruments capable of receiving it. The LIGO collaboration did not announce their discovery immediately. The scientists understood the magnitude of what they believed they had detected, and they understood equally well the importance of being certain, of checking and rechecking every aspect of the measurement before making any public claim. A false announcement, a mistaken claim of discovery, would be deeply damaging to the credibility of the entire field, and so the collaboration embarked upon a rigorous and painstaking process of verification. They examined the data from both detectors, looking for any signs of instrumental artifacts or environmental disturbances that might have mimicked a gravitational wave signal. They ran their analysis pipelines again and again, testing different methods and comparing results. They considered every possible alternative explanation, every potential source of error, every conceivable way in which they might have fooled themselves. This process of verification took 5 months. For 5 months, more than 1,000 scientists around the world kept the secret, continuing their work, refining their analyses, preparing their papers, all while the outside world remained unaware of what had been found. It was an extraordinary exercise in collective discipline, a testament to the scientific culture of caution and rigor that the collaboration had cultivated over many years. Rumors began to circulate, as rumors always do, and there was speculation in the scientific community and in the press that LIGO might have detected something significant, but the collaboration maintained its silence until they were ready. On February 11, 2016, the LIGO Scientific Collaboration held a press conference in Washington, D.C., to announce their results to the world. The room was filled with journalists and scientists, cameras and microphones, all waiting to hear what the collaboration had to say. David Rates, the executive director of the LIGO laboratory, stepped to the podium and spoke the words that so many had been waiting to hear. "We have detected gravitational waves," he said. "We did it." The room erupted in applause, and the news spread rapidly around the globe, carried by television and radio and the countless channels of the internet. A century after Einstein had first predicted their existence, gravitational waves had been directly observed. The universe had a new voice, and we had learned to listen. On the 17th of August in the year 2017, at precisely 12 hours and 41 minutes Coordinated Universal Time, the detectors at Hanford in Washington State and Livingston in Louisiana both registered the arrival of gravitational waves from a distant corner of the universe, and in the hours and days that followed, this detection would become the most thoroughly observed astronomical event in the history of science, involving more telescopes, more satellites, more observatories, and more scientists than any cosmic occurrence before or since, and it began, as these things do, with the gentlest of tremors passing through the fabric of spacetime itself. The signal that arrived on that August day was different from the gravitational wave detections that had come before, and the difference was apparent almost immediately to the automated systems monitoring the data streams from both detectors, because where the mergers of black holes had produced signals lasting only fractions of a second, this new signal persisted for approximately 100 seconds, a long and gradually rising chirp that swept upward through the sensitive frequency band of the instruments, beginning at around 24 Hz and climbing steadily higher as the sources responsible for the waves drew closer and closer together in their final orbital dance, and this extended duration told the scientists something important about the nature of the objects involved, namely that they were less massive than the black holes detected previously, and the careful analysis of the waveform soon revealed that the two objects spiraling together had masses of approximately 1.46 and 1.27 times the mass of our Sun, placing them squarely within the range expected for neutron stars, those extraordinarily dense remnants of massive stars that have exhausted their nuclear fuel and collapsed under their own gravity. The source of these gravitational waves lay in a galaxy catalogued as NGC 4993, a lenticular galaxy situated in the constellation Hydra, at a distance of approximately 130 million light-years from Earth, which is to say that the light and gravitational waves from this event had been traveling through the expanding universe for 130 million years before reaching our planet and our instruments on that August day, and during all that time the two neutron stars had long since completed their merger, and whatever remnant they left behind had settled into its final state. And yet for us the event was only just beginning to unfold, a cosmic story told in waves of gravity and light that arrived after a journey of unimaginable duration across the vastness of intergalactic space. What made this detection so remarkable was not merely that gravitational waves had been observed from the collision of neutron stars, though that alone would have been a significant achievement, but rather that just 1.7 seconds after the gravitational wave signal reached its peak, indicating the moment when the two neutron stars finally touched and merged, the Fermi Gamma Ray Space Telescope, orbiting high above the Earth's atmosphere, detected a short burst of gamma radiation. Arriving from the same general region of the sky, and this near-simultaneous detection of gravitational waves and electromagnetic radiation from the same cosmic event marked the beginning of what astronomers call multi-messenger astronomy, the observation of a single phenomenon through fundamentally different means, like hearing a distant thunderclap and seeing the lightning flash that caused it, each messenger carrying its own particular information about the event that produced it. The gamma ray burst detected by Fermi was classified as a short gamma ray burst, lasting approximately 2 seconds, and for many years astronomers had theorized that such short bursts might be produced by the merger of compact objects like neutron stars, but until this moment there had been no way to confirm this hypothesis directly, and now here was the confirmation arriving in the form of gravitational waves and gamma rays from the same event separated by less than 2 seconds, a delay that itself carried information about the physics of the merger and the processes by which the gamma rays were produced in the violent aftermath of the collision. In the minutes following the detection, an alert was sent out to observatories around the world, informing astronomers that a gravitational wave event had been observed and that there was reason to believe it might have an electromagnetic counterpart visible to traditional telescopes, and this alert set in motion one of the largest coordinated observation campaigns in the history of astronomy, with approximately 70 observatories on every continent and in space turning their instruments toward the region of sky where the source was believed to be located, and the urgency was considerable because any optical emission from the event would be expected to fade relatively quickly, and the opportunity to observe it would not last indefinitely. The task of locating the precise position of the gravitational wave source on the sky was aided considerably by the fact that the Virgo detector in Italy, though less sensitive than the two LIGO instruments, had also been operating at the time of the detection, and while the signal in the Virgo data was weak, the combination of data from all three detectors allowed for a much better determination of the source direction than would have been possible with LIGO alone, through a process called triangulation that relies on the tiny differences in arrival time of the signal at each detector, and this three-detector analysis narrowed the probable location of the source to a region of approximately 28 square degrees on the sky, which is still a considerable area to search, roughly equivalent to 140 full moons, but far smaller than the hundreds or thousands of square degrees that would have been indicated by the two LIGO detectors operating without Virgo. Approximately 11 hours after the gravitational wave detection, as night fell over the mountains of Chile where several major observatories are located, the Swope telescope at Las Campanas Observatory became the first to identify the optical counterpart of the gravitational wave source, observing a new point of light in the outskirts of the galaxy NGC 4993 where no star had been visible before, and this discovery was made by a team of astronomers who had been systematically searching the galaxies within the probable sky region identified by the gravitational wave analysis, reasoning that the source was most likely to be found in association with a known galaxy rather than in the empty spaces between them. The new light source, which was given the designation AT2017 GFO but became known more commonly as the Kilonova associated with gravitational wave event 170817, was initially blue-white in color and remarkably luminous, shining with approximately 1,000 times the brightness of a typical nova, those smaller stellar explosions that occur in certain binary star systems, and yet it was distinctly less luminous than a supernova, placing it in a category of transient astronomical phenomena that had been theorized but never before observed, and the name kilonova, suggesting something 1,000 times more powerful than a nova, seemed appropriately descriptive of its intermediate nature. In the hours and days that followed, telescopes around the world and in orbit above the atmosphere observed the kilonova across the entire electromagnetic spectrum, from radio waves to X-rays, and the observations revealed something quite extraordinary about the nature of this event. For the light being emitted was not merely the cooling glow of heated gas, but rather the signature of newly created heavy elements being forged in the aftermath of the neutron-star merger, elements that had not existed moments before the collision and that were now being produced in staggering quantities through a process that nuclear physicists call the rapid neutron capture process, or R process for short. The R process is one of the two main mechanisms by which elements heavier than iron are produced in the universe, the other being the slow neutron capture process or S process that occurs in the interiors of certain evolved stars, and for many decades the site of the R process had been uncertain, with supernovae being the leading candidate, but the observations of the Kilonova associated with gravitational wave event 170817 provided compelling evidence that neutron-star mergers are in fact responsible for a significant fraction, perhaps even the majority, of the R process elements in the universe. As the two neutron stars merged, the intense gravitational forces tore material from their surfaces and flung it outward into space at a significant fraction of the speed of light, and this ejected material was extraordinarily rich in neutrons, having come from the dense neutron-rich interiors of the colliding stars, and in this neutron-rich environment the conditions were exactly right for the R process to occur, with atomic nuclei rapidly capturing neutrons and building up to heavier and heavier elements before the captured neutrons could decay, producing elements all the way up to and beyond uranium in the periodic table. Among the elements created in this single event were gold and platinum, those precious metals that humans have valued for millennia, and the observations indicated that the Kilonova produced approximately 10 Earth masses of gold and a similar quantity of platinum, along with countless other heavy elements including europium, strontium, and many others, all synthesized in a matter of seconds from the neutron-rich matter expelled during the merger, and while these quantities may seem modest on a cosmic scale, the discovery confirmed that over the billions of years of the universe's history, countless such mergers have seeded the galaxies with heavy elements, including those that eventually found their way into the planets and into the very atoms that make up our bodies. The color of the Kilonova changed over the following days, shifting from blue-white to red as the expanding cloud of newly created elements cooled and as heavier elements with more complex atomic structures came to dominate the emission, and this color evolution matched the predictions of theoretical models remarkably well, providing confidence that the physics of the R process was being correctly understood and that neutron-star mergers were indeed the long-sought site of heavy element production. Beyond the insights into nuclear physics and element formation, the gravitational wave detection combined with the observation of the host galaxy NGC 4993 allowed astronomers to make an independent measurement of a fundamental cosmological quantity known as the Hubble constant, which describes the rate at which the universe is expanding, and this measurement was possible because the gravitational wave signal provided a direct determination of the distance to the source, independent of any assumptions about the brightness of the objects involved, while the redshift of the host galaxy provided information about how fast it was receding from us due to the expansion of space, and by combining these two pieces of information the astronomers could calculate the Hubble constant directly, opening a new window onto one of the most important and contentious questions in modern cosmology. The scientific output from this single event was extraordinary in its scope and its collaborative nature, with more than 4,000 individual authors contributing to the papers published in the weeks and months following the detection, representing institutions and observatories from around the world, and the sheer number of contributors reflects both the complexity of the observations and the global nature of the astronomical community that had prepared for years to respond to exactly such an event, with observation plans and communication protocols already in place so that when the alert went out, the response was rapid and coordinated. And so the detection of gravitational wave event 170817 marked a turning point in the young field of gravitational wave astronomy, demonstrating that the observation of gravitational waves could be combined with traditional astronomical techniques to reveal aspects of the universe that neither approach could have uncovered alone. And as you rest now and let these thoughts settle gently into your mind, you might consider how remarkable it is that the collision of two neutron stars 130 million years ago, long before humans existed on this planet, could produce both the gravitational waves that reached our detectors and the heavy elements that may well be present in the very room where you now lie, gold perhaps in jewelry or in the electronics nearby, atoms forged in ancient cosmic cataclysms and now part of the quiet world around you as you drift slowly toward sleep. On the 3rd of October, in the year 2017, the Royal Swedish Academy of Sciences gathered in Stockholm to announce the Nobel Prize in Physics, and the news that emerged from that stately room carried with it the weight of a century's worth of dreaming and decades of painstaking work, and the quiet persistence of thousands of people who had devoted their careers to listening for whispers from the distant universe. The prize that year would go to 3 scientists whose names had become synonymous with gravitational wave detection, though the story behind those names, and behind the collaboration they represented, was far richer and more complex than any single announcement could convey, and in the telling of it we find not only triumph but also the bittersweet edges that so often accompany great achievements, the people who contributed but could not be named, and the questions that arise when science becomes too large, too collective, too profoundly collaborative to fit within the traditional frameworks of individual recognition. The laureates announced that autumn morning were Rainer Weiss of the Massachusetts Institute of Technology, and Kip Thorne and Barry Barish of the California Institute of Technology, and together they would share the prize for decisive contributions to the LIGO detector and the observation of gravitational waves, words that the committee chose carefully to acknowledge both the technological achievement and the scientific discovery that had followed from it. Rainer Weiss received one half of the prize, while Thorne and Barish shared the other half between them, a division that reflected, in the committee's judgment, the particular nature of their respective contributions, though such divisions are always somewhat artificial when applied to work that spans so many decades and involves so many intertwined efforts. To understand what Rainer Weiss brought to this endeavor, one must travel back not only through the years of his scientific career but to the very beginning of his life, to the circumstances that shaped him before he ever set foot in a laboratory or contemplated the nature of spacetime. Weiss was born in Berlin in 1932, into a family that would soon find itself in grave danger, for his father was Jewish and the shadow of National Socialism was lengthening across Germany with each passing year. When Rainer was still a young child, his family fled, first to Prague and then, as the darkness spread across Europe, onward to the United States, arriving in New York City when he was just a boy of 6 or 7, carrying with them the particular resilience of refugees, the knowledge that safety is not guaranteed, that one must make one's place in the world through effort and adaptation. This early experience of displacement, of starting over in a new country with a new language and new uncertainties, would shape Weiss in ways that perhaps even he could not fully articulate, instilling in him both a fierce independence and a certain scrappiness, a willingness to build things with his own hands and to trust his own judgment even when others doubted him. His path to scientific eminence was not a straight one, and there is something rather comforting in this fact, something that reminds us that great careers are not always marked by early and obvious success. Weiss enrolled at MIT as an undergraduate student, drawn to physics and to the tangible work of building instruments, but his first attempt at university did not go well, and he failed out. His academic career seemingly ended before it had properly begun. The reasons for this early stumble were various, involving distractions and misplaced energies that are common enough among young people finding their way, and yet Weiss did not allow this setback to define him. He returned to MIT, completed his studies, and gradually found his footing in the world of experimental physics, developing a particular talent for the kind of precise, careful measurement that would become his life's work. It was Weiss who, in 1972, produced the foundational technical analysis of how a laser interferometer might be used to detect gravitational waves, a document that laid out not only the basic concept but also the sources of noise that would need to be overcome, a kind of blueprint for the decades of development that would follow. His contribution was not merely theoretical but deeply practical, rooted in the understanding of real instruments and real limitations, the sort of knowledge that comes only from years of working with one's hands as well as one's mind. Kip Thorne's role in the story was of a rather different character, for Thorne was a theoretical physicist, a student and interpreter of Einstein's equations, who brought to the collaboration a deep understanding of what gravitational waves should look like and what sources in the universe might produce them in detectable quantities. While Weiss concerned himself with the exquisite challenges of building a detector, Thorne concerned himself with questions of what that detector should be looking for, translating the abstract mathematics of general relativity into concrete experimental requirements, calculating the waveforms that would result from colliding black holes or merging neutron stars, and helping to establish the theoretical targets that would guide the experimentalists in their work. This translation between theory and experiment is a subtle and demanding art, for it requires not only mastery of the mathematics but also an understanding of what is practically achievable, and Thorne performed this bridging role with grace and persistence over many years, helping to ensure that the theoretical and experimental efforts remained connected and mutually informing. Barry Barish came to the project somewhat later than Weiss and Thorne, but his contribution was no less essential, for it was Barish who transformed LIGO from a struggling, dysfunctional project into a functioning large-scale scientific enterprise capable of actually detecting gravitational waves. When Barish took over as director of LIGO in 1994, the project was in serious trouble, plagued by internal conflicts, management difficulties, and doubts from the scientific community and funding agencies about whether it could ever succeed. Barish brought to the task a wealth of experience in what is sometimes called big science, the kind of large-scale collaborative research that had become common in particle physics, where enormous accelerators and detectors require the coordinated efforts of hundreds or thousands of scientists and engineers working together toward common goals. He had worked on major particle physics experiments, understood the organizational structures and management practices that such efforts required, and applied this knowledge to LIGO with considerable skill, restructuring the collaboration, clarifying responsibilities, rebuilding relationships with funding agencies, and generally putting the project on a footing that allowed it to move forward. Without Barish's steady hand during those difficult years, it is quite possible that LIGO would have faltered and failed, that the detectors would never have been built to the sensitivity required, and that the gravitational waves from that distant black hole merger would have passed through the Earth unnoticed, as so many others had done before. And yet the announcement of these three laureates carried with it an absence that many in the scientific community felt keenly, for there was a fourth founder of LIGO who did not share in the prize, a Scottish physicist named Ronald Drever, whose contributions to the project had been profound and essential. Drever had been one of the early pioneers of laser interferometer gravitational wave detection, had developed key techniques for stabilizing the lasers and improving the sensitivity of the instruments, and had been one of the three principal investigators, along with Weiss and Thorne, who had originally proposed LIGO to the National Science Foundation. But by the time the Nobel Committee made its decision, Drever could not be included, for the Nobel Prize is awarded only to the living, and Drever had passed away in March of 2017, just 7 months before the announcement. His death followed years of struggle with dementia, a cruel illness that had gradually stolen from him the brilliant mind that had contributed so much to the field, and there is a particular sadness in the timing of it all, the way that just a few months separated him from recognition that would have been richly deserved. The rules of the Nobel Prize are clear and long-standing on this matter, permitting no posthumous awards except in the rare circumstance where a laureate dies after the announcement but before the ceremony, and so Drever's name was absent from the honors bestowed that October day, a reminder of the arbitrary cruelties that time can inflict even upon the most deserving. The limitation of the Nobel Prize to no more than 3 recipients has long been a source of discussion and occasional controversy in the scientific community, for modern science is increasingly a collaborative enterprise, conducted not by solitary geniuses working alone in their studies but by large teams of researchers who contribute in myriad ways to shared achievements. The LIGO scientific collaboration, at the time of the detection, comprised more than 1,000 scientists and engineers from institutions around the world, people who had built the detectors and maintained them, who had developed the data analysis pipelines and the theoretical models, who had worked on seismic isolation systems and laser stabilization and mirror coatings, and 100 other specialized tasks essential to the whole. When the Nobel Committee honored 3 individuals for decisive contributions, it was not diminishing the work of these 1,000 others, but the structure of the prize itself, rooted in an earlier era of science when individual contributions were more readily identifiable, struggled to accommodate the reality of what LIGO represented. This tension between individual recognition and collective achievement called to mind, for many observers, an earlier episode in the history of physics prizes, one that had become emblematic of the ways in which the Nobel framework could fail to capture the full picture of scientific discovery. In 1974, the Nobel Prize in Physics had been awarded for the discovery of pulsars, those remarkable rotating neutron stars that emit beams of radiation sweeping across the cosmos like lighthouse beacons. The prize that year went to Anthony Hewish, who had led the research group, and to Martin Ryle, for their pioneering work in radioastrophysics, but notably absent from the recognition was Jocelyn Bell, the graduate student who had actually made the discovery, who had noticed the strange regular pulses in the data and brought them to attention, who had done the painstaking work of operating the telescope and analyzing its output. Bell's exclusion from the 1974 prize became one of the most discussed omissions in Nobel history, a case that many felt illustrated the tendency to overlook the contributions of junior researchers, and of women in particular, in favor of more senior male scientists. In the decades that followed, Jocelyn Bell Burnell, as she became known after her marriage, conducted herself with remarkable grace regarding this exclusion, declining to express bitterness and indeed speaking thoughtfully about the complexities of attribution in collaborative science. When LIGO's detection was announced and the Nobel Prize followed, Bell Burnell offered her perspective on the matter, praising the way that the LIGO collaboration had handled questions of credit and recognition. She noted that while the Nobel Prize necessarily went to individuals, the collaboration itself had been careful to emphasize the collective nature of the achievement, to ensure that the hundreds of contributors received acknowledgement even if they could not share in the formal prize. This was, in her view, a healthier model than the one that had prevailed in earlier eras, a recognition that modern science is a team endeavor and that even when prizes must be given to individuals, the culture surrounding those prizes can either reinforce or counteract the misleading impression that great discoveries are the work of lone geniuses. Among the many members of the LIGO collaboration who played crucial roles in the detection and its announcement was Gabriela González, an Argentine physicist who served as the spokesperson for the collaboration during the period when the first detection was made and verified. González had the responsibility of coordinating the response to the detection, of ensuring that the analysis was conducted properly, that the results were checked and rechecked, and that the announcement was made in a way that accurately represented both the science and the collaborative effort behind it. Her leadership during those intense months of verification and preparation was essential to the success of the endeavor, and her presence at the forefront of the announcement helped to illustrate the international and diverse nature of the collaboration, a community of scientists drawn from many countries and backgrounds, united by their shared commitment to listening for the faint ripples of distant cataclysms. The Nobel Prize of 2017 was, in the end, both a celebration and a simplification, a recognition that honored 3 individuals while standing, however imperfectly, for the work of many more. The committee acknowledged this implicitly in its citation, which spoke of contributions to the LIGO detector as well as to the observation itself, suggesting that the prize was meant to honor an achievement that no single person, or even 3 persons, could have accomplished alone. And in the gentle aftermath of the announcement, as congratulations flowed and speeches were prepared, the larger community of gravitational wave scientists continued their work, for there were more signals to detect, more sources to understand, more secrets of the universe waiting to be uncovered by the patient instruments they had built together, instruments that would go on listening through the long nights, sensing the tremors of spacetime that carry news of events beyond imagining, in a cosmos that reveals its wonders slowly, one whisper at a time. In the countryside near Pisa, where the land slopes gently toward the Ligurian Sea and the vineyards stretch in patient rows beneath the Tuscan sun, there stands a scientific instrument of remarkable precision, its long arms extending across the agricultural landscape in a quiet collaboration between the ancient practice of winemaking and the modern pursuit of understanding the universe. This is Virgo, the European gravitational wave detector, and its presence among the olive groves and grape arbors of the Cascina commune represents one of the most fruitful partnerships in contemporary physics, a joining of French and Italian scientific traditions that began in the early 1990s and has since contributed immeasurably to our comprehension of the cosmos. The Virgo collaboration was formally established in 1993, when researchers from France and Italy came together with a shared vision of detecting the subtle ripples in spacetime that Einstein had predicted so many decades before. The name itself was chosen with a certain poetry appropriate to the instrument's location, referencing the Virgo cluster of galaxies, that dense gathering of perhaps 2,000 gravitational systems located some 50 million light-years from our own Milky Way, a region of space where one might reasonably expect dramatic cosmic events to occur with some regularity. The founders of this collaboration understood that detecting gravitational waves would require not only extraordinary technical achievement but also the kind of sustained international cooperation that transcends national boundaries and individual careers, a commitment to a goal that might take decades to achieve. The site selected for Virgo lies in the municipality of Cascina, a small town in the province of Pisa where the terrain is flat enough to accommodate the detector's considerable footprint, and where the geological conditions provide reasonably stable ground upon which to build such a sensitive instrument. The detector itself consists of two perpendicular arms, each extending 3 kilometers across the Tuscan landscape, somewhat shorter than the 4-kilometer arms of the American LIGO detectors but nonetheless capable of extraordinary sensitivity. These arms house vacuum tubes through which laser light travels, bouncing between mirrors suspended with exquisite care, measuring distances with a precision that defies ordinary comprehension. Construction of Virgo proceeded through the 1990s and into the early 2000s, a gradual accumulation of infrastructure and expertise that transformed a patch of Italian farmland into one of the most sensitive scientific instruments ever constructed. The detector became operational in 2007, joining the global effort to detect gravitational waves at a time when such detection remained theoretical rather than demonstrated. 4 years, Virgo listened to the universe alongside its American counterparts, recording data, refining techniques, and waiting for the cosmos to deliver a signal strong enough to be measured. When the first gravitational wave detection occurred in September of 2015, Virgo was temporarily offline for upgrades, undergoing the improvements that would eventually make it even more sensitive than before. But by August of 2017, when two neutron stars spiraled together in a galaxy some 130 million light-years distant, Virgo had rejoined the observing network, and its participation in that detection proved crucial in ways that demonstrated the profound value of having multiple detectors spread across the globe. The neutron star merger of August 2017, designated GW 170817 in the careful nomenclature of gravitational wave astronomy, arrived at each of the 3 operational detectors at slightly different times, the differences measured in mere milliseconds but carrying enormous informational content. Because Virgo was operating that day, astronomers were able to triangulate the source of the gravitational waves with unprecedented precision, narrowing down the region of sky where the merger had occurred to a patch small enough that optical telescopes could search for the accompanying light. This triangulation was possible because gravitational waves, like all waves, travel at finite speed, and a wave originating from a particular direction in space will reach detectors at different locations on Earth at measurably different moments. With only 2 detectors, as had been the case for the first gravitational wave detection in 2015, the possible source locations form a ring across the sky, a band of uncertainty that encompasses a vast area and makes follow-up observations with conventional telescopes enormously challenging. But with 3 detectors, those rings of possibility intersect in a much smaller region, reducing the search area from thousands of square degrees to perhaps tens or even fewer. The addition of Virgo to the August 2017 detection reduced the uncertainty in the source location by a factor of approximately 10, transforming an impossible search into a merely difficult one, and enabling the historic observation of both gravitational waves and electromagnetic radiation from the same cosmic event. Far from the vineyards of Tuscany, in the mountains of central Japan, another gravitational wave detector has been constructed under circumstances quite different from those of its European and American counterparts. This is Kagra, an instrument whose very name encapsulates its unique characteristics, combining the Japanese word for divine spirit with the first letters of gravitational wave. Kagra represents a different approach to the challenge of isolating such a delicate instrument from the tremors and vibrations of our restless planet, an approach that involves going underground, deep into the ancient rock of the Japanese Alps, where the seismic noise that plagues surface-based detectors is naturally attenuated by the sheer mass of overlying stone. The Kumioka mine, located in Gifu Prefecture in the mountainous heart of Honshu, has a long history of scientific repurposing, having previously hosted the Super Kamiokande neutrino detector, an instrument that itself contributed to Nobel Prize-winning research on the fundamental properties of these ghostly particles. The decision to locate Kagra in this same geological setting, some 200 meters beneath the surface of the mountain, reflects the understanding that certain scientific measurements require an isolation from ordinary environmental noise that simply cannot be achieved at the surface, no matter how sophisticated the vibration-damping technology employed. At such depths, the constant small movements of the Earth's surface, caused by everything from ocean waves breaking on distant shores to the footsteps of animals and humans going about their daily activities, are reduced to a fraction of their surface intensity. The rock itself acts as a filter, absorbing and dissipating the energy of these vibrations before they can reach the detector's sensitive components. This natural seismic isolation allows KAGRA to achieve sensitivity at low frequencies that would be difficult or impossible to match with surface-based instruments, opening a window onto gravitational wave sources that might otherwise remain hidden. But the underground location of KAGRA is not its only distinguishing feature. The detector also employs cryogenic cooling of its primary mirrors, reducing their temperature to approximately 20 Kelvin, which is to say some 250 degrees Celsius below the freezing point of water. At such temperatures, the random thermal motion of atoms within the mirror material is dramatically reduced, diminishing a source of noise that fundamentally limits the sensitivity of room temperature detectors. The mirrors themselves are fashioned from sapphire, a material chosen for its excellent thermal and optical properties at cryogenic temperatures, its ability to conduct heat efficiently while maintaining the precise surface figure required for interferometric measurements. KAGRA began its first observing run in February of 2020, joining the global network just as the world was beginning to grapple with circumstances that would temporarily curtail many human activities, scientific observation included. The initial sensitivity of the instrument was modest compared to its design goals, but the achievement of bringing such a complex system into operation represented a significant milestone, demonstrating that underground cryogenic gravitational wave detection was not merely a theoretical possibility but a practical reality. Meanwhile, on the other side of the globe, plans have long been developing to add yet another node to this expanding network of cosmic listening posts. LIGO India, formally approved in 2016 following years of discussion and planning, will bring a third LIGO-type detector online, identical in design to the instruments in Louisiana and Washington state but located in the Hingoli district of Maharashtra, in the western reaches of the Indian subcontinent. The site selected near the village of Aunda offers the geological stability and isolation from human activity required for such sensitive measurements, while the latitude and longitude of the location provide maximum benefit for the triangulation of gravitational wave sources. The addition of LIGO India to the global network, anticipated in the late 2020s following completion of construction and commissioning, will dramatically improve the ability of astronomers to pinpoint the origins of gravitational wave signals. With 5 major detectors operating simultaneously, spread across 4 continents and offering multiple baselines of different lengths and orientations, the localization of sources will improve by yet another significant factor, transforming the relatively coarse sky maps of today into the precise positional measurements required for detailed multi-messenger astronomy. There exists as well a smaller but scientifically valuable instrument in Germany, known as GEO 600, its name reflecting the 600-meter length of its arms. Located near Hanover in Lower Saxony, GEO 600 has served since its construction in the 1990s as a crucial testbed for advanced technologies, a place where new ideas can be tried and refined before being implemented in the larger detectors. Many of the innovations that now enhance the sensitivity of LIGO and Virgo were first demonstrated at GEO 600, including sophisticated techniques for squeezing the quantum properties of light to reduce measurement noise below what classical physics would seem to permit. The importance of having multiple detectors extends beyond the obvious benefit of source localization. Each detector, no matter how carefully constructed, is subject to occasional spurious signals, brief disturbances caused by everything from minor earthquakes to passing trucks to the settling of equipment, signals that might momentarily mimic the signature of a passing gravitational wave. With a single detector, distinguishing such false alarms from genuine cosmic events would be essentially impossible, as there would be no independent check on the validity of any particular measurement. But with 2 or more detectors operating simultaneously, the situation changes fundamentally. A genuine gravitational wave, propagating across the Earth, will produce correlated signals in all operational detectors, arriving at each location at times consistent with the wave's direction of travel and separated by intervals no greater than the light travel time between the instruments. A local disturbance at one detector, by contrast, will produce no corresponding signal at the others, revealing itself immediately as a false alarm to be disregarded. This requirement for coincidence between multiple detectors provides an enormously powerful filter against spurious signals, allowing researchers to identify genuine gravitational wave events with high confidence. The improvement in scientific capability that comes from expanding the network from 2 detectors to 5 is not merely additive but multiplicative, each new instrument providing not just one additional measurement but multiple new baselines when combined with all existing detectors. 2 detectors provide 1 baseline, 3 detectors provide 3 baselines, 4 detectors provide 6 baselines, and 5 detectors provide 10 distinct baselines, each offering different sensitivity to gravitational waves arriving from different directions. This geometric increase in baseline diversity translates directly into improved angular resolution for source localization, transforming the relatively large uncertainty regions of 2 detector observations into the compact, well-defined patches required for efficient electromagnetic follow-up. The global network of gravitational wave detectors thus represents a scientific instrument of truly planetary scale, its components distributed across continents and connected not by physical infrastructure but by the shared purpose of listening to the universe's most violent events. From the vineyards of Tuscany to the mountains of Japan, from the bayous of Louisiana to the high plains of eastern Washington, from the farmland of India yet to host its detector, this network spans the Earth in a web of laser light and suspended mirrors, each node contributing its own perspective on the gravitational wave sky. And so the expansion continues, quietly, methodically, without fanfare or drama, as scientists and engineers in multiple countries work toward the common goal of improving our ability to hear the universe. Each new detector that comes online, each incremental improvement in sensitivity, each refinement of technique and technology, brings us closer to a comprehensive understanding of the gravitational wave sky, revealing events and phenomena that would otherwise remain forever hidden from our perception, occurring in the depths of space where only gravity can carry the news of their occurrence to our waiting instruments. When the first gravitational wave signal arrived at the detectors in September of 2015, the scientists who analyzed its properties found themselves confronted with something rather unexpected, something that would gently reshape our understanding of how the universe creates its heaviest stellar remnants. The 2 black holes that had spiraled together and merged, releasing that first detected ripple across spacetime, were each around 30 times the mass of our Sun, and when they combined they formed a single black hole of approximately 6 to 2 solar masses, with the remaining 3 solar masses worth of energy radiating outward as gravitational waves. These were, to put it simply, much larger black holes than most astronomers had anticipated finding in such a merger, and this gentle surprise marked the beginning of a new era in which gravitational wave observations would reveal a population of black holes quite different from what our theories had prepared us to expect. To understand why these masses were so surprising, we might briefly consider how stellar mass black holes were thought to form before the gravitational wave era began. When a very massive star exhausts its nuclear fuel and can no longer support itself against gravity, it collapses inward in a catastrophic event we call a supernova, and if the collapsing core is massive enough, it will form a black hole rather than a neutron star. The black holes we had previously observed in our galaxy, detected through their gravitational influence on companion stars or through the X-rays emitted by material falling onto them, tended to have masses clustering around 10 to 15 times that of our Sun, with few examples reaching much beyond 20 solar masses. Theoretical models of stellar evolution, which carefully track how stars burn through their fuel and shed their outer layers through stellar winds, generally suggested that black holes much heavier than this would be difficult to produce, particularly in environments with higher concentrations of heavy elements, because such stars would lose much of their mass to these powerful winds before they could collapse. Yet here were 2 black holes, each around 30 solar masses, having found each other somewhere in the cosmos and merged. This observation suggested that somewhere in the universe, conditions existed that allowed for the formation of these heavier black holes, perhaps in regions where stars contained fewer heavy elements and therefore experienced weaker stellar winds, retaining more of their mass until the moment of collapse. This possibility pointed toward black hole formation in the early universe or in certain pockets of galaxies where the chemical enrichment from previous generations of stars had been less thorough. The first detection, catalogued as GW150914, was therefore not merely a confirmation of Einstein's century-old prediction, but also an invitation to reconsider our models of how massive stars live and die. As the detectors continued their observations across multiple observing runs, the catalogue of gravitational wave events grew steadily larger, and with each new detection the picture of the black hole population became incrementally clearer, though also in some ways more puzzling. By the end of the third observing run in early 2020, the LIGO and Virgo collaborations had accumulated over 90 confident detections of gravitational wave events, the vast majority of which were mergers involving black holes, either two black holes spiraling together or, in a handful of precious cases, other combinations involving neutron stars. This growing collection of events allowed scientists to begin studying the statistical properties of the black hole population, examining not just individual remarkable cases but the overall distribution of masses, spin rates, and other characteristics. One of the more intriguing events in this growing catalogue arrived in May of 2019 and was designated GW190521. This signal revealed a merger involving black holes of approximately 85 and 66 solar masses, combining to form a remnant black hole of roughly 142 solar masses. The larger of the two original black holes, at 85 solar masses, presented a particular puzzle, because according to our understanding of stellar physics, black holes in a certain mass range should be extremely difficult or perhaps impossible to create through the normal collapse of a single massive star. This forbidden zone, sometimes called the pair instability gap, arises from a peculiar process that occurs in the cores of very massive stars. When a star is sufficiently massive, the temperatures in its core can become so extraordinarily high that the energetic photons begin to spontaneously convert into pairs of electrons and their antimatter counterparts, positrons. This conversion removes pressure support from the core, causing it to contract and heat further, which triggers explosive nuclear burning. For stars in a certain mass range, this process leads to violent pulsations that eject enormous amounts of material, preventing the formation of a black hole in the approximate range of 50 to 130 solar masses. Stars below this range can collapse into black holes of up to perhaps 40 or 50 solar masses, while stars above this range are so massive that they collapse directly into black holes of 130 solar masses or more, skipping the pair instability process entirely. But the intermediate range, roughly 50 to 130 solar masses, should be empty, a gap in the black hole mass distribution where stellar evolution simply cannot place them. Yet GW190521 appeared to contain a black hole of 85 solar masses, sitting squarely within this forbidden gap. This observation invited several possible explanations, each with its own implications for our understanding of the cosmos. One possibility is that the black hole formed not from the collapse of a single star, but from the merger of two smaller black holes at some earlier time, a process called hierarchical merging. In this scenario, two black holes each below the pair instability gap could have merged to form a black hole within the gap, and this product could then have found another black hole partner and merged again, which is the event we detected. Such hierarchical mergers would most likely occur in dense stellar environments where black holes are abundant and have opportunities to encounter one another multiple times, places like the centers of globular clusters or the nuclear star clusters at the hearts of galaxies. Another possibility, more speculative but deeply fascinating, is that some of these unexpectedly massive black holes could be primordial in origin, formed not from collapsing stars but from density fluctuations in the very early universe, mere fractions of a second after the Big Bang. If regions of the infant cosmos were sufficiently dense, they could have collapsed directly into black holes without ever passing through the stellar phase, and such primordial black holes could in principle have any mass, unconstrained by the rules of stellar evolution. While the evidence for primordial black holes remains circumstantial, the detection of black holes in unexpected mass ranges keeps this possibility alive as an area of ongoing investigation. The statistical picture emerging from the first three observing runs revealed other surprises beyond individual remarkable events. When scientists examined the overall distribution of black hole masses, they found that the population did not spread evenly across all possible masses, but instead showed certain preferences, with an apparent peak around 8 to 10 solar masses and another feature around 35 solar masses. The detailed shape of this distribution carries information about the physics of stellar collapse, the environments where binary black holes form, and the processes that bring them together. Understanding why black holes prefer certain masses will keep astrophysicists occupied for many years to come. The spins of the detected black holes also proved somewhat unexpected. Before the gravitational wave detections began, some models predicted that black holes in merging binaries might be spinning quite rapidly and that their spins might be preferentially aligned with the orbital axis of the binary system, especially if the two black holes had formed from stars that were originally orbiting each other. However, the observations revealed that many of the detected black holes had relatively low spin rates, and their spin orientations appeared to be somewhat randomly distributed rather than neatly aligned. This finding suggests that at least some of the merging black holes may have come together through dynamical processes in dense stellar environments, where black holes capture each other gravitationally after the fact, rather than evolving together from a binary star system from birth. The spin measurements remain somewhat uncertain for individual events, but the population-level trends provide valuable clues about the formation channels that produce merging black hole pairs. Among the individual events that taught us something new about gravitational wave physics, GW 190412 stands out for its unequal mass ratio. This merger involved black holes of approximately 30 and 8 solar masses, a ratio of nearly 4 to 1, making it the first clearly asymmetric black hole merger detected. When two black holes of similar mass merge, the gravitational wave signal is dominated by a single frequency that rises over time as the objects spiral closer. But when the masses are significantly unequal, the signal contains additional frequency components called higher harmonics, much as a musical note contains overtones in addition to its fundamental frequency. The detection of these higher harmonics in GW 190412 provided a new way to test our theoretical models of gravitational wave emission and opened possibilities for more precise measurements of source properties in future asymmetric mergers. The first three observing runs also delivered detections of an entirely different flavor, mergers involving not two black holes but a black hole and a neutron star. In January of 2020, two events designated GW 200105 and GW 200115 provided the first confident observations of neutron star black hole mergers. These systems represent a kind of cosmic middle ground between the binary black hole mergers that dominated the catalog and the binary neutron star merger detected in 2017. In each of these events, a neutron star, the dense remnant of a less massive star, spiraled into a black hole and was swallowed. The black holes in these systems were relatively small, around 6 to 9 solar masses, and the neutron stars were approximately 1.5 to 2 solar masses, consistent with what we know of neutron star masses from other observations. Unlike the famous neutron star merger of 2017, these neutron star black hole events did not produce detected electromagnetic counterparts, which was not entirely unexpected given the mass ratios involved. When a neutron star merges with a black hole that is sufficiently massive, the neutron star may be swallowed whole, plunging across the event horizon before it can be tidally disrupted and spread into a disk of material that might power observable light. The absence of electromagnetic signals from these events was therefore consistent with our models, though future detections with different mass ratios may yet reveal neutron star black hole mergers accompanied by observable light and perhaps the creation of heavy elements through rapid neutron capture. The possibility of hierarchical mergers, black holes merging and then merging again, has become an increasingly important concept for interpreting the growing catalogue of detections. In most regions of the universe, black holes that form from stellar collapse would simply drift through space, unlikely to encounter another black hole closely enough to merge within the age of the universe. But in certain dense environments, gravitational interactions can bring black holes together more efficiently. Globular clusters, those ancient spherical collections of hundreds of thousands of stars bound tightly together, provide one such environment. In the crowded cores of these clusters, black holes can sink toward the center through a process called mass segregation, accumulating in a small region where they frequently interact. Through a series of gravitational encounters, black holes can be paired into binaries that eventually merge, and the merger products can sometimes be retained in the cluster rather than being kicked out by the recoil from asymmetric gravitational wave emission, allowing them to find new partners and merge again. The hierarchical merger scenario provides a natural explanation for black holes appearing in the pair instability gap, as successive mergers can build up black hole masses beyond what single stellar collapse can achieve. It also predicts certain signatures in the spin distributions of the detected population, since black holes formed through mergers tend to have spins around a particular value determined by the orbital dynamics of the merger, typically around 0.7 in the dimensionless spin parameter that physicists use. Finding black holes with spins clustering around this value, particularly among the more massive black holes, would provide supporting evidence for the hierarchical merger pathway. As the catalogue of gravitational wave detections continues to grow with each new observing run, the picture of the black hole population becomes richer and more detailed, full of gentle surprises that invite us to refine our theories and imagine the diverse environments where these dark objects form and find each other across cosmic time. As we have seen throughout our journey together, the detectors currently listening for gravitational waves represent extraordinary achievements of human ingenuity, with their 4-kilometer arms stretching across the landscapes of Louisiana and Washington and Italy and Japan, catching the faint tremors of distant cosmic collisions. And yet, as remarkable as these instruments are, they can only hear a portion of the gravitational wave spectrum, rather like having ears that detect only the middle octaves of a piano while the deep bass notes and the highest treble remain forever silent. The universe is singing in frequencies both higher and lower than our current detectors can perceive, and so scientists around the world are designing new instruments, new observatories, and new methods to listen to these unheard portions of the cosmic symphony, and it is to these future endeavors that we now turn our attention, with their promise of revealing phenomena we can barely imagine from our present vantage point. Perhaps the most ambitious of these planned instruments is the Laser Interferometer Space Antenna, known by its gentle acronym LISA, which will extend the principle of interferometric detection to a scale that simply cannot be achieved on the surface of our planet. While LIGO's arms stretch 4 kilometers from end to end, LISA will create a triangular formation of 3 spacecraft separated by 2.5 million kilometers each, which is to say roughly 6.5 times the distance from the Earth to the Moon, floating in the quiet darkness of space where no seismic vibration or passing truck could ever disturb their delicate measurements. The 3 spacecraft will follow the Earth in its orbit around the Sun, trailing behind our planet by about 50 million kilometers, and they will exchange laser beams across the vast emptiness between them, measuring the distances to one another with a precision that seems almost dreamlike in its ambition. When a gravitational wave passes through this enormous triangle, the distances between the spacecraft will change by amounts smaller than the diameter of an atom, and yet the instruments aboard will be sensitive enough to detect these infinitesimal stretches and squeezes in the fabric of spacetime itself. The European Space Agency, working in collaboration with NASA, has been developing LISA for many decades now, and the mission is currently planned to launch around the year 2035, when 3 identical spacecraft will be carefully placed into their positions and begin their long, patient vigil listening for the low-frequency gravitational waves that ground-based detectors cannot hear. The frequencies that LISA will detect range from about 1/10,000th of a hertz to about 1 hertz, which corresponds to gravitational waves with periods ranging from a few seconds to several hours, oscillations so slow that the entire Earth would ring like a bell many times during a single cycle of the wave. To test the technologies required for such an ambitious mission, the European Space Agency launched a Pathfinder spacecraft called LISA Pathfinder in 2015, and the results exceeded even the most optimistic expectations, demonstrating that it is indeed possible to shield small test masses so perfectly from external disturbances that they float in an almost pure state of free fall, isolated from everything except the gentle undulations of spacetime itself. The lower frequencies that LISA will detect correspond to sources quite different from those observed by LIGO and Virgo, and it is in this difference that much of the scientific excitement lies. When supermassive black holes merge, black holes with masses of millions or even billions of times the mass of our Sun that lurk at the centers of galaxies, they produce gravitational waves with very long periods, waves that oscillate over minutes or hours rather than the fractions of a second characteristic of the stellar mass black hole mergers detected from the ground. Such events occur when galaxies themselves collide and merge, as we know they frequently do over the vast timescales of cosmic evolution, and the central black holes of the merging galaxies eventually spiral together in a dance that releases more energy in gravitational waves than all the stars in both galaxies combined. LISA will be able to detect such mergers from anywhere in the observable universe, allowing astronomers to witness the formation of the largest black holes and to trace the history of galaxy mergers back to the earliest epochs of cosmic time. But LISA will not merely wait for dramatic merger events to occur, for the universe at lower frequencies is alive with continuous sources, thousands of compact binary systems emitting their steady gravitational hum simultaneously, creating a kind of cosmic background noise that will fill the detector at all times. Within our own galaxy alone, there are expected to be tens of millions of binary systems consisting of white dwarf stars orbiting one another with periods of minutes to hours, and thousands of these will be individually detectable by LISA, their gravitational wave signals standing out from the background like distinct voices in a choir. Scientists have already identified several of these systems through their electromagnetic emissions, and they know precisely what gravitational wave frequency and amplitude LISA should detect, making them perfect verification sources, guaranteed signals that will confirm the detector is working as designed when it begins its observations. Meanwhile, on the ground, plans are advancing for a new generation of gravitational wave detectors that will far surpass the capabilities of LIGO and Virgo and Kagra, instruments of such sensitivity that they will detect black hole mergers not occasionally, as current detectors do, but continuously, catching every such event in the observable universe and constructing a complete census of the cosmic population of colliding compact objects. In Europe, the Einstein telescope project proposes to build an underground detector in the shape of an equilateral triangle, with each side measuring 10 kilometers in length, buried several hundred meters beneath the surface of the Earth where seismic disturbances are greatly reduced and the temperature remains stable throughout the seasons. The triangular configuration is particularly clever because it allows the detector to measure both polarizations of gravitational waves simultaneously, and by placing multiple interferometers within the same underground tunnels, operating at different frequencies, the Einstein telescope will achieve a sensitivity roughly 100 times greater than current detectors across a broad range of gravitational wave frequencies. Several sites in Europe are being considered for the Einstein telescope, including locations in the Netherlands, in Sardinia, and along the border of Belgium and Germany, and the geological and logistical studies required to choose the final site continue with their careful, methodical pace. The underground construction will be an enormous undertaking, requiring the excavation of tunnels stretching 30 kilometers in total, and the installation of vacuum systems and laser optics and seismic isolation platforms of unprecedented scale and precision. Yet the scientific rewards justify such efforts, for the Einstein telescope would detect every binary neutron-star merger within a significant fraction of the observable universe, accumulating thousands of events per year that would revolutionize our understanding of the dense nuclear matter inside neutron stars, the production of heavy elements, and the ultimate fate of massive stars. Across the Atlantic, scientists in the United States are developing plans for an even larger detector called Cosmic Explorer, which would extend the basic design of LIGO to arms 40 kilometers in length, 10 times longer than the current instruments. The longer arms mean that the physical displacement caused by a gravitational wave is proportionally larger and therefore easier to measure, and Cosmic Explorer would achieve sensitivities comparable to the Einstein telescope while using a more conventional L-shaped configuration that simplifies certain aspects of the construction and operation. The current vision involves building 2 such detectors in the United States, separated by thousands of kilometers to enable precise localization of gravitational wave sources on the sky, and together with the Einstein telescope and possibly other advanced detectors around the world, these instruments would form a global network of extraordinary capability, a permanent gravitational wave observatory monitoring the cosmos with constant vigilance. But not all gravitational wave detectors require the construction of new instruments, for nature has provided us with remarkably precise clocks scattered throughout the galaxy, and by monitoring these natural clocks with sufficient care, we can detect gravitational waves at frequencies far lower than even LISA will observe. Pulsars are rapidly rotating neutron stars that emit beams of radio waves from their magnetic poles, and as they spin, these beams sweep across the Earth like the rotating beam of a lighthouse, producing pulses of radio emission that arrive with extraordinary regularity. Some millisecond pulsars, which rotate hundreds of times per second, are so stable that their pulse arrival times can be predicted years in advance with a precision of a few hundred nanoseconds, and it is this stability that makes them useful as gravitational wave detectors. When a very low-frequency gravitational wave passes through the space between a pulsar and the Earth, the distance changes ever so slightly, and the pulses arrive either a little earlier or a little later than predicted, and by monitoring many pulsars spread across the sky over many years, scientists can search for the correlated patterns of timing variations that would reveal the presence of gravitational waves with periods of years or even decades. The NANO-GRAVE collaboration in North America, along with similar groups in Europe, Australia, and Asia, has been conducting precisely such observations for more than 15 years now, patiently accumulating timing measurements of dozens of the most stable millisecond pulsars in the galaxy. And in June of 2023, These collaborations announced that they had found compelling evidence for a background of gravitational waves permeating the universe at nanohertz frequencies, waves with periods measured in years, most likely produced by pairs of supermassive black holes orbiting one another in the centers of distant galaxies, slowly spiraling together over millions of years before their eventual merger. This detection, achieved not with lasers and mirrors but simply with radio telescopes and patient record-keeping, represents a remarkable confirmation that gravitational waves fill the cosmos at all frequencies, a continuous background hum of spacetime oscillations produced by the largest objects in the universe. Beyond all these planned and operational detectors lies an even more ambitious dream, the hope of detecting primordial gravitational waves produced in the earliest moments of the universe itself. According to the theory of cosmic inflation, the universe underwent a period of exponentially rapid expansion in the first tiny fraction of a second after the Big Bang, and this violent stretching of spacetime should have generated gravitational waves that still echo through the cosmos today, frozen into the structure of spacetime like ripples preserved in ice. In 2014, a team of scientists announced that they had detected the signature of these primordial waves in the polarization of the cosmic microwave background radiation, the ancient light left over from when the universe was only 400,000 years old, and for a brief moment it seemed that one of the greatest predictions of inflationary cosmology had been confirmed. But subsequent analysis revealed that the signal was not primordial gravitational waves after all, but rather the effect of dust within our own galaxy polarizing the microwaves in ways that mimicked the expected signature, and the search for these elusive primordial ripples continues with improved instruments and more careful attention to galactic foregrounds. When all these future observatories begin their operations, the scientific landscape will be transformed in ways we can only partially anticipate. The Einstein telescope and Cosmic Explorer will detect every stellar mass black hole merger in the observable universe, thousands of events per year, allowing statistical studies of black hole populations and their evolution over cosmic time. These detectors will observe the gravitational waves from merging black holes with such precision that they will be able to test general relativity in regimes where gravity is extraordinarily strong, searching for any deviations from Einstein's predictions that might point toward new physics beyond our current understanding. They will even be able to map the space-time geometry around individual black holes by observing how the gravitational wave signal is modified as it passes through the strong gravitational fields near these objects, providing a detailed picture of the curved spacetime that Einstein first described over a century ago. LISA will observe the births of supermassive black holes, the inspirals of compact objects into these giants, and the background rumble of countless binary systems throughout the galaxy, while pulsar timing arrays will continue to monitor the slow dance of the most massive black hole pairs in the universe, pairs that take millions of years to complete a single orbit around one another. And somewhere in all this data, there may be surprises we cannot yet imagine, phenomena that current theories do not predict, signals from objects or events that we have not yet conceived of, for the history of astronomy is filled with examples of new instruments revealing entirely unexpected wonders, and there is no reason to think that gravitational wave astronomy will be any different. For now, we can rest content knowing that the universe is filled with gravitational waves at all frequencies, from the rapid chirps of colliding neutron stars to the slow undulations of merging supermassive black holes, from the cosmic background of countless overlapping sources to perhaps even the ancient echoes of inflation itself, and that human beings are building the instruments to hear them all, one patient observation at a time, extending our senses ever deeper into the fabric of space-time as we listen to the universe reveal its secrets in gentle oscillations of nothing more substantial than empty space and time itself.